Picture a world painted in shades of rust and ochre, where towering volcanoes dwarf any mountain on Earth, and vast canyons stretch across the landscape like ancient scars. This is Mars, a planet that has captivated human imagination for centuries, not just as a distant point of light in the night sky, but as a place of profound mystery and possibility. From early astronomers sketching its surface through telescopes to modern scientists guiding rovers across its dusty plains, Mars has always beckoned us with questions. What secrets lie buried beneath its red soil? Could it have once harbored life, or does it still? Every image sent back from its surface feels like turning a page in a cosmic detective story. And with each new discovery, we inch closer to understanding our place in the universe. Now, imagine joining an expedition across this alien terrain, where every rock and dune holds the potential to rewrite textbooks. Thanks to decades of robotic exploration, from the intrepid rovers like Curiosity and Perseverance to orbiters mapping the planet from above, we've uncovered clues that are as baffling as they are breathtaking. Some findings challenge everything we thought we knew about Mars, while others hint at stories yet untold. Strange formations that look eerily familiar, chemical signatures that suggest ancient habitable environments, and even glimpses of what might be evidence of past life. This isn't just about scientific data. It's about piecing together the history of a world that may have once been far more Earth-like than we ever dared to dream. In this video, we're embarking on a journey to explore 30 of the most bizarre, puzzling, and awe-inspiring discoveries ever made on the Red Planet. From unexplained geological oddities to potential signs of ancient rivers and lakes, each finding invites us to question, wonder, and imagine. Whether you're a space enthusiast or simply curious about the mysteries beyond our world, you're about to witness a side of Mars that few have ever seen, a place where science and speculation collide, and where every snapshot from millions of miles away brings us closer to answering one of humanity's oldest questions: are we alone in the cosmos? So settle in, open your mind to the possibilities, and let's dive into the wonders waiting for us on Mars. Our journey into the bizarre begins with perhaps the most famous Martian mystery of all time, an image that captured the world's imagination and launched 1,000 conspiracy theories. In 1976, NASA Viking 1 orbiter was diligently mapping the Cydonia region of Mars, taking photographs to help select future landing sites. Among the thousands of frames of barren, cratered landscape, one image stood out. It appeared to show a colossal humanoid face, nearly 2 miles from end to end, staring blankly up at the cosmos from the rusty soil below. The face on Mars was born. With its seemingly symmetrical eyes, nose, and a mouth set in a stoic expression, it looked less like a geological feature and more like a monument, a sphinx of another world. The public and media went into a frenzy, interpreting it as undeniable proof of a long-lost intelligent civilization. Could it be a relic, a warning, a tombstone for an entire planet? The idea that we were not alone in the universe suddenly felt tantalizingly close. This powerful reaction we had to that grainy Viking image has a name: Pareidolia. It's the innate, hardwired tendency of the human brain to find familiar patterns, especially faces, in random stimuli. We see the man in the moon, a scowling visage in the front of a car, or the Virgin Mary on a piece of toast. It's a survival mechanism. From infancy, recognizing a face, whether friendly or threatening, is one of the most important skills we have. So when we turned our cameras to Mars, it was almost inevitable that we would project our own image onto that alien world. The face wasn't a hoax, but a trick of the mind and light, a combination of low-resolution imaging and the sun's angle at that particular moment, casting shadows that created the illusion of carved features. For over 2 decades, the face remained a controversial enigma, a favorite topic for books and television specials arguing for ancient astronauts. The mystery wasn't truly solved until the late 1990s and 2000s, when new spacecraft like Mars Global Surveyor arrived with far superior cameras. They aimed their high-resolution lenses at Cydonia for a second look, and the iconic face dissolved before our eyes. The new images revealed what was really there: a perfectly natural, albeit strikingly shaped, mesa, a large hill with a flat top, heavily eroded by billions of years of wind and dust storms. The haunting symmetry was gone, replaced by the lumpy, irregular contours of a rock formation. The shadows that once defined a mouth and eyes were just shadows, and from a different angle or with better light, the face simply vanished. Science had provided an answer, yet for many, the romance of the idea has never completely faded, a testament to our deep desire to find connection in the cosmos. From the grand illusion of a colossal face, we turn to a discovery that was small in stature but monumental in its implications. Just a few years after the new millennium began, a little rover named Opportunity bounced to a stop on the Meridiani Planum, a flat plain squarely on the Martian equator. Its mission was to search for clues about water, and it didn't have to look far. As the dust settled from its airbag-cushioned landing, the rover's cameras sent back the first close-up images of its new home. The ground wasn't just covered in fine red dust. It was littered with millions of tiny, grayish, spherical objects. They were scattered everywhere like marbles or ball bearings, and the science team immediately gave them a memorable nickname: blueberries. These weren't edible, of course, but their perfectly round shape was utterly fascinating. How did nature create something so uniformly spherical on a planet known for its jagged rocks and random dunes? Opportunity's onboard instruments got to work, and analysis revealed their true nature. The blueberries were concretions, solid nodules of the mineral hematite. On Earth, hematite typically forms in the presence of liquid water. These Martian versions were created over vast stretches of time when mineral-rich water seeped through the porous sandstone, dissolved particles of hematite, and then redeposited them in layers around a central nucleus, like a grain of sand, growing slowly outward in all directions to form a near-perfect sphere. This process is a telltale sign of a past environment that wasn't just briefly wet, but persistently so, with water lingering for perhaps thousands or even millions of years. The sheer abundance of these blueberries was the real shock. They were embedded in the bedrock and then eroding out, covering the landscape like a carpet of evidence. Their presence was one of the first tangible, physical proofs that Mars didn't just have fleeting puddles or ice. It once had an active, watery chemistry operating at or just below its surface. This was a quieter, more scientific revelation than the face on Mars, but in many ways it was far more profound. While one was a trick of light and psychology, the other was a physical artifact telling a concrete story of a different Mars, a world that could have been habitable for microbial life. The blueberries became silent, stone witnesses to a planet with a past that was not just alien, but in some ways strangely familiar. While the blueberries were a slow and steady revelation of Mars's watery past, the Opportunity rover would later serve up a mystery that was far more immediate and utterly baffling. After a decade of rolling across the Martian surface, the veteran rover was preparing to take a series of photographs of the same spot to help scientists track atmospheric changes. One set of images showed barren, familiar soil, but just 12 Martian days later, a new photo revealed something that absolutely was not there before: a rock that seemed to have fallen out of the sky. It was small, pale on the outside with a deep red, jelly-like center, and it was sitting right in the middle of an otherwise empty patch of ground. The internet, of course, went wild, immediately dubbing it the jelly donut for its uncanny resemblance to the powdered pastry. How did it get there? Did it roll down a hill? Was it ejected by a distant meteor impact? Or was this, as some more fringe theories suggested, evidence of something more biological? The most thrilling and immediate hypothesis was that the rover itself had uncovered it. A close examination of the area showed a small, disturbed patch of soil, not far from the rock's new location. The leading theory became that as opportunity was maneuvering, one of its wheels likely scrubbed against the ground, flipping this singular stone up and out of the dirt, landing it perfectly within the rover's field of view. It was a mundane explanation, but it made perfect sense. Further analysis by the rover's alpha particle X-ray spectrometer confirmed the rock's composition was high in sulfur and magnesium, and it had doubled the amount of manganese than any other rock previously studied on Mars. This unique chemical signature suggested it had been formed in the presence of water, a relic from a wetter time that had been buried just beneath the surface, hidden from view for possibly billions of years until a robot from Earth accidentally unearthed it. Yet, the initial moment of mystery holds a special place in the story of Martian exploration. It underscores the dynamic and sometimes unpredictable nature of the planet. While we often picture Mars as a static, dead world, things do move. Winds shift sands, rocks tumble, and on this occasion, a robotic geologist played a role in the action. The Jelly Donut episode was a perfect storm of public engagement and scientific process. It captured our collective imagination with a genuine, "What is that?" moment, demonstrating how a simple, natural occurrence on another world can feel deeply strange and wonderful to us back on Earth. It was a reminder that even after 10 years of incredible discoveries, Mars was still capable of pulling a fast one on us, serving up a fresh puzzle that required a little bit of old-fashioned detective work to solve. Just as the Jelly Donut showed us how a simple shift in perspective can create a mystery, our next discovery proves that our minds are always searching for the familiar, even in the most alien of landscapes. Rovers have sent back countless images of rocks in every shape and size, but one particular formation, captured by the Curiosity rover in 2018, caused a minor internet sensation. Perched on the side of a low ridge was a formation that, from just the right angle and with a little imagination, bore a startling resemblance to the head of a coyote or a small fox. But the comparison that truly captured the public's imagination was to the Great Sphinx of Giza. With what appeared to be a rounded headdress, a defined brow, and a pointed chin, it looked less like a random rock and more like a weathered statue watching over the Gale crater. For a moment, it felt as if we had stumbled upon a monument from a lost civilization, a silent guardian of Mars's secrets. This phenomenon, where we see a sphinx, a face, or even a rodent in the rocks, is a perfect example of Pareidolia in action once again. It's that same powerful, subconscious instinct that made the face on Mars so compelling. Our brains are incredible pattern recognition machines, constantly filtering the chaos of the world around us to identify potential threats, sources of food, or other people. This skill is so deeply ingrained that it operates on autopilot, often finding significance in completely random shapes. On Earth, we see it in cloud formations or the gnarled bark of a tree. On Mars, a planet we are intensely curious about, we are primed to look for anything that breaks the monotony of a barren landscape, and our minds eagerly fill in the gaps, turning a curiously eroded rock into a potential artifact. Far from being a nuisance, these moments of mistaken identity are actually valuable opportunities for science communication. When an image like the Martian Sphinx goes viral, planetary geologists seize the chance to explain the very real and fascinating processes that created it. They point out that what we're seeing is not a carving, but the work of billions of years of erosion. The relentless Martian wind carrying fine, abrasive dust acts like a natural sandblaster, slowly and patiently sculpting the bedrock. Combine that with other forces like temperature fluctuations that cause rocks to crack and split, and you have a natural artist capable of creating an infinite variety of shapes. The Sphinx is just one fleeting masterpiece in this ongoing gallery, a shape that will continue to erode and change until eventually it looks like nothing more than a pile of rubble. These instances remind us that the true wonder of Mars isn't about finding things that look like what we've left behind on Earth. The real magic lies in understanding the natural processes that are utterly alien to us. The wind on Mars behaves differently because the atmosphere is so thin. The temperature swings are more extreme. The very chemistry of the rocks is unlike anything in our terrestrial experience. So when we see a sphinx, it's a fun diversion, a testament to our own creativity. But when scientists explain how that shape was formed, we are granted a deeper, more profound insight into the mechanics of an entire world. It shifts the narrative from a search for familiar ghosts to an appreciation of Mars on its own extraordinary terms. A planet with a geological story every bit as rich and complex as our own. Even the most advanced robotic explorers are not immune to leaving a little litter behind. A fact hilariously driven home by the Curiosity rover in 2012. As it was preparing to use its robotic arm for the first time to sift some soil, its mast camera snapped a picture of the ground. There, amidst the familiar rusty red sand and pebbles, was something that glinted back at the camera with a brilliant, metallic sheen. It was small, perhaps no larger than a pebble itself, but its polished, bright appearance was completely alien against the dull, ancient Martian terrain. For a moment, it sparked a wave of excited speculation online. Had Curiosity found a piece of metallic ore, a strange mineral formation, or something even more unexpected? The mystery was solved with almost comical speed by the mission team at the Jet Propulsion Laboratory. This wasn't a Martian treasure at all. It was a tiny shred of plastic that had fallen off the rover itself. More specifically, it was a piece of benign debris from the rover's complex descent and landing system, likely a bit of wire casing or a fragment from the protective sheath that guarded the rover during its dramatic sky crane maneuver. The object's shiny appearance was simply due to it being a modern, human-manufactured material, utterly unlike any naturally occurring rock or mineral on the red planet. It was a classic case of looking for the extraordinary and finding the incredibly mundane, a tiny piece of Earth that had hitched a ride across space. This incident, while amusing, highlights a critically important and ongoing aspect of rover operations: forensic self-monitoring. Every time a rover moves its arm, drills into a rock, or even just drives over a patch of soil, there's a potential to generate or uncover debris. The teams on Earth meticulously track every component of the rover, and they spend a significant amount of time poring over images to identify any foreign object. Is that a piece of Martian bedrock, or is it a fragment of aluminum that shook loose from the rover's wheel? Is that a strange new soil type, or is it a piece of insulating material? Distinguishing between human-made litter and a genuine Martian discovery is a fundamental part of the daily scientific process. A mistaken identification could lead to a wild goose chase, wasting precious time and energy, or worse, contaminate a sensitive chemical analysis with earthly material. This constant vigilance is about more than just keeping a tidy workspace. It's a cornerstone of planetary protection. One of the primary goals of these missions is to search for evidence of past or present life, which involves detecting organic molecules, the carbon-based building blocks of life. If a rover were to accidentally drop a minuscule piece of plastic or a flake of human skin, and then later detect its own trash, it could mistakenly announce a monumental discovery that was, in fact, just a piece of itself. By carefully cataloging every bit of debris, the mission teams create a sort of background noise map, allowing them to recognize and ignore contamination, ensuring that any potential discovery of organics is truly Martian in origin. So, while that shiny object was a brief and funny footnote, it perfectly illustrates the painstaking care and forensic detail that goes into the extraordinary process of exploring another world, one careful observation at a time. Now we turn to a discovery that seemed to offer a literal invitation into the unknown. a moment where the line between geology and fantasy became impossibly thin. In May of 2022, the Curiosity rover was navigating the slopes of Mount Sharp, its cameras scanning the sedimentary layers of the Greenhugh pediment. One of its navigation cameras captured a wide-angle image of a cliff face, and when the raw image was beamed back to Earth, one feature immediately leaped out. There, set into the rock, was a near-perfect rectangular opening, complete with a sharp, dark shadow cast within. It looked less like a natural crack and more like a deliberately carved doorway, a secret entrance leading deep into the heart of the Martian mountain. The internet predictably erupted. Was it a tomb, a shelter, a gateway to a subterranean world? The human mind, ever eager for narrative, immediately began crafting stories about what, or who, might have built it. The truth, as revealed by the patient work of geologists, is both less fantastical and no less fascinating. This doorway is a beautiful example of a natural geological fracture. On a planet without plate tectonics like Earth, the primary forces shaping the landscape over billions of years have been the slow, relentless stresses of the planet's cooling and shrinking core, and the immense weight of overlying rock. These forces create immense pressure, and that pressure has to go somewhere. It frequently releases by fracturing the bedrock, creating sharp, clean cracks and fissures. The remarkably straight lines and right angles we see are not a sign of intelligence, but a testament to the uniformity of these deep-seated stresses acting on a homogeneous block of rock. The process is identical to the way mud dries and cracks in a grid pattern, just on a monumental, planetary scale. What makes this particular fracture so visually striking is the role of erosion. Mars is a world scoured by wind. Fine, abrasive dust carried on the breeze has been sandblasting these cliffs for eons. This wind erosion selectively wears away at the exposed surfaces, widening natural cracks and accentuating their features. In this case, the wind has meticulously cleaned out the fractured opening and undercut the area above it, creating a pronounced lintel or overhang that casts a deep, inviting shadow. The perfect right angles are simply the result of the fracture propagating through the rock in the most mechanically efficient way possible. And the wind has done the rest of the work, sculpting it into a form that our pattern-seeking brains instantly recognize as artificial. This phenomenon taps into a deep and persistent human desire, the search for shelter and the mystery of what lies beyond a threshold. A doorway is one of the most powerful symbols in our psyche. It represents transition, possibility, and the unknown. It promises a way in, a place of safety, or a hidden secret waiting to be uncovered. When we see that shape on another world, all those ancient instincts fire at once. We aren't just looking at a rock. We are projecting our own stories onto it, imagining ourselves walking through that opening to discover what's on the other side. It's a daydream of exploration that is fundamentally, wonderfully human. Ultimately, the doorway serves as a perfect metaphor for our entire relationship with Mars. It represents the tantalizing allure of the planet, constantly hinting at secrets just out of view. But it also reminds us that the real wonder isn't in finding something that looks like it was made for us. The true marvel is in deciphering the natural, alien processes that created it. That clean fracture and the wind-scoured opening tell a profound story about the internal mechanics of Mars and the incredible patience of its atmosphere. They speak of a world that operates on its own terms, following physical laws we understand, yet creating outcomes that never fail to astonish us. The doorway may not lead to a hidden chamber, but it opens a window into the magnificent and utterly foreign geology of the Red Planet. Moving from grand illusions of doorways to the discovery of something small and delicate, we find that some of Mars's most profound statements are whispered, not shouted. In February of 2022, the Curiosity rover focused its Mars Hand Lens imager on a patch of rock known as Glen Torridon, a region believed to have been rich with clay minerals formed in ancient water. The stunningly detailed close-up revealed something that felt instantly out of place. A tiny, beautiful formation no larger than a penny, with delicate, crystalline structures that looked almost exactly like a piece of coral or a small, branching flower. In a landscape dominated by dust, sand, and rugged stone, this fragile, complex object was a breathtaking sight. It wasn't a sign of life, but its intricate form felt distinctly organic, a piece of abstract art crafted by nature itself. This exquisite feature is a spectacular example of what geologists call a diagenetic feature. Diagenesis refers to the chemical, physical, and biological changes that sediments undergo after they are first deposited, but before they turn into hard, solid rock. In this case, the story likely began billions of years ago when this area of Mars was a lake bed or a stream, with layers of fine sediment settling at the bottom. As that sediment was buried, mineral-rich water began to percolate through it. Within that water were dissolved compounds, perhaps sulfates or other salts. When the chemical conditions were just right, a change in acidity, temperature, or pressure, those dissolved minerals began to come out of solution, solidifying into crystals. The branching, flower-like shape is the key to understanding its formation. The minerals didn't just precipitate as a solid lump. They likely grew from a single nucleation point, extending outward in multiple dimensions, pushing the surrounding sediment aside as they grew. This process creates what are known as crystal aggregates or concretions with intricate, dendritic, or tree-like patterns. The final, stunning shape was then exposed after eons of wind erosion patiently blew away the softer, surrounding sedimentary rock that once encased it, leaving the more resilient mineral formation standing in delicate relief. It's a fossil, not of life, but of a chemical process that occurred in water long ago. The significance of this tiny Martian flower is monumental. Its very existence provides a hyper-detailed record of the aqueous environment in which it formed. The specific minerals involved can tell scientists about the chemistry of that ancient water. Was it salty, acidic, neutral? This information is crucial for determining the past habitability of Mars, as certain chemical environments are more favorable to life as we know it than others. Furthermore, the process of diagenesis often creates pore spaces and microhabitats within rocks. On Earth, such spaces can be havens for microbial life, protecting them from harsh surface conditions. Finding these features on Mars suggests that not only was there water present, but the subsurface environment may have been a potentially protective niche where life could have gained a foothold and perhaps even been preserved. Ultimately, the flower is a powerful symbol of the new era of Martian exploration. We are no longer just confirming the presence of past water. We are forensic geologists, examining the crime scene of a vanished world with incredible precision. We're moving from asking, was there water, to what kind of water was it and what was happening within it? This tiny, intricate formation, smaller than a coin, tells a more vivid story about the dynamic, interactive chemistry of ancient Mars than 1,000 images of dry riverbeds. It reminds us that sometimes, the most important discoveries aren't the largest or the loudest, but the small, quiet ones that require us to look closely to hear the secrets they have held for billions of years. Imagine not just finding a rock that looks like a flower, but an entire landscape that appears to have been forged in myth. From the intimate, close-up view of a rover, we now pull back to an orbital perspective, where the Mars Reconnaissance Orbiter's powerful high-rise camera has captured one of the most visually stunning and geologically perplexing terrains on the Red Planet. In the rugged region of Arabia Terra, the orbiter spotted a vast area of rock that looks less like a planet's crust and more like the hide of a colossal, slumbering beast. The surface is a chaotic mosaic of interlocking bluish-gray plates, each one outlined with razor-sharp ridges. The texture is so strikingly reptilian that scientists didn't hesitate to give it the perfect name, the dragon-scale terrain. It's a landscape that feels both ancient and alive, a place where the very ground seems to tell a story of immense, primal forces locked in a battle between fire and water. Unraveling the mystery of how this fantastical landscape came to be is a bit like being a planetary detective. Geologists have a few compelling theories, each one pointing to a dramatically different chapter in Mars's history. One leading hypothesis involves the planet's fiery volcanic past. The thinking is that this area was once flooded by massive, repeated flows of lava. As these immense sheets of molten rock cooled and solidified from the top down, they would have contracted and cracked, much like drying mud. But instead of a simple grid, the constant pressure from newer lava flows pushing against the older, solidifying crust could have compressed and fractured it into these enormous interlocking plates. The deep, recessed areas might be where the rock has been weathered away, while the raised, scaly ridges represent the more resilient material, hardened against eons of erosion. But there's another, even more tantalizing possibility that involves the other key ingredient for life: water. Some scientists see the dragon's scales and think not of lava, but of a process called convection that can happen in thick, muddy sediments. On Earth, this occurs on the floors of ancient lakes or shallow seas. When a layer of wet, mineral-rich mud is heated from below by geothermal activity, it can begin to churn slowly. Denser, cooler mud sinks, while warmer mud rises, creating a cellular pattern of convection currents. As this system stabilizes and the sediments finally cement into rock, it can preserve that swirling, polygonal pattern. If this is the case on Mars, the dragon-scale terrain could be the fossilized footprint of a vast, ancient body of water. A muddy lakebed that was actively churning with heat and chemistry billions of years ago. This would make it not just a geological curiosity, but a prime candidate in the search for signs of past habitability. The third great sculptor of Mars, the wind, also likely played a crucial role in finishing this masterpiece. Regardless of whether the primary structure was built by lava or mud, the incredible detail we see today is almost certainly due to the planet's relentless, sand-blasting winds. For millions of years, fine, abrasive dust has been scouring across this landscape, acting as a natural etcher. The wind would have preferentially worn away the softer rock within the scales, deepening the gaps and simultaneously polishing the harder, raised ridges, sharpening them into the dramatic, defining features that catch the sunlight from orbit. This eons-long sandblasting session is what gave the terrain its final, breathtaking definition, turning a broad geological structure into a landscape of intricate, dragon-like armor. This bizarre and beautiful terrain is far more than just a pretty picture. It's a crucial piece in the giant jigsaw puzzle of Martian history. Its very existence, and the debate over its origin, forces scientists to ask fundamental questions about the environment of ancient Mars. Was this region once dominated by violent, repetitive volcanism that shaped the planet's surface? Or was it a place of standing water, of churning mud pots and lakebeds that could have been a cradle for life? The dragon-scale terrain presents us with two very different, equally profound versions of Mars's past. By studying its mineral composition and exact structure, we can start to rule out one story in favor of the other. Each theory leads us down a different path toward understanding the planet's climate, its capacity to support life, and the awesome forces that have shaped it into the world we see today. It's a powerful reminder that the most alien landscapes often hold the keys to the most fundamental truths. Leaving behind the dragon-scaled plains of Arabia Terra, our journey takes us to a different kind of Martian mystery, one that speaks of absence rather than presence, of a landscape defined by what is no longer there. In the vast, flat regions of Noctis Labyrinthus and Hellas Basin, orbital cameras have captured images of thousands of peculiar, elongated craters. They look like giant, hollowed-out footprints or the negative impressions of huge, teardrop-shaped blobs, all arranged in sweeping, organized patterns across the terrain. These are not impact sites from asteroids, but something far more ethereal and revealing. They are the ghost dunes, To understand a ghost dune, we must first picture its living counterpart. Imagine a massive sand dune, hundreds of feet tall, marching slowly across the Martian landscape billions of years ago, shaped by powerful, consistent winds, just like dunes in the Sahara on Earth. Now, imagine a cataclysmic event, a flood of water, or perhaps a shower of volcanic ash that suddenly inundates the area, burying the base of these immense dunes in a layer of wet sediment or fine ash. This material is rich in minerals that, when exposed to water or simply over time, act as a natural cement. It hardens around the dune's lower flanks, creating a perfect, rock-hard mold of the dune's shape. The dune itself, however, is just sand. Millennia later, the winds shift, and they begin to scour the landscape again. This time, they have the power to erode the uncemented sand making up the bulk of the dune, but they cannot break apart the hardened, cemented mold at its base. The sand is blown away, grain by grain, leaving behind an empty, inverted cast in the rock, a hauntingly precise silhouette of the dune that once was. These ghostly impressions are more than just geological curiosities. They are frozen snapshots of an ancient environment. Their very shape is a wind vane pointing directly into the past. The classic crescent form of a Martian dune, for example, always points its tips downwind. By measuring the orientation of thousands of these ghost dune casts, scientists can effectively map the prevailing wind directions from billions of years ago, reconstructing the atmospheric circulation patterns of a younger Mars. This tells us if the winds were consistent and strong, or variable and weak, providing critical data for modeling the planet's ancient climate. Furthermore, the existence of these features tells a profound story about a dramatic shift in Martian history. The fact that they were preserved at all means that the conditions on Mars changed drastically and suddenly. The atmosphere had to be thick enough to support winds powerful enough to move massive amounts of sand and build enormous dunes. Then, that same atmosphere had to essentially vanish, becoming the thin, wispy envelope it is today. The event that buried their bases, likely a sudden inundation of water, was a punctuation mark in this story, a brief, violent episode that captured their forms just before the planet dried out for good. They are the tombstones of a lost climate, marking the grave of a thicker, more dynamic atmosphere that could have made the surface of Mars a very different place. Perhaps most tantalizingly, these hollow spaces could be keeping a secret. On Earth, the protected, shaded interiors of sand dunes are known to be microhabitats for certain types of hardy microbes, sheltering them from the harsh ultraviolet radiation and extreme temperatures at the surface. The ghost dunes of Mars, with their hardened, rocky shells and hollow, sheltered interiors, would have provided a similar protected environment for billions of years. If microbial life ever did gain a foothold on Mars, these empty casts could have been the perfect place for it to retreat and perhaps even preserve evidence of its existence. They represent not just a record of wind and water, but a potential time capsule, a locked safe in the desert of Mars that may still hold a biological secret within its stony walls. While the ghost dunes tell a story of a planet that lost its atmosphere, our next discovery reveals a world that is still dynamically active today, sculpting its surface in a way that is utterly alien to our own experience. Near the Martian South Pole, orbiting spacecraft have captured images of a landscape that seems to have leaped straight from a science fiction nightmare. Fanning out across the rusty terrain are vast, dark, dendritic patterns that look uncannily like a swarm of gigantic spiders crawling across the red soil, their spindly legs radiating out from a central point. This is areniform terrain, areniform literally meaning spider-like, and it is one of the most bizarre and actively forming geological features we've found anywhere in the solar system. The secret to these Martian spiders isn't life, but a seasonal dance of ice and gas that occurs nowhere on Earth. During the long, dark Martian winter, temperatures at the poles plummet so drastically that carbon dioxide, which makes up the majority of the thin atmosphere, freezes solid directly onto the surface, forming a layer of translucent CO2 ice that can be several feet thick. When the sun returns in the spring, something incredible happens. Sunlight penetrates this slab of clear, solid carbon dioxide ice and heats the dark Martian soil trapped beneath it. This soil warms up, but the ice above it remains solid. Eventually, the heat conducted from the ground causes the bottom of the CO2 ice slab to sublimate. That is, it transforms directly from a solid back into a gas, skipping the liquid phase entirely. Trapped between the ground and the heavy slab of ice above it, this gas has only one way to go: up. The pressure builds and builds until it becomes immense, finally finding a weak point in the overlying ice and explosively bursting through in a high-pressure jet. These jets can be powerful enough to hurl dark sand and dust from the surface high up into the Martian atmosphere, creating great, dark geysers that can be seen from orbit. But the most lasting effect is what happens at the point of eruption. As the pressurized gas forces its way out, it carves a narrow channel through the ice and scours the softer ground beneath, leaving behind a deep, dark, branching fissure. Over countless Martian springs, this process repeats itself in the same spots, with gas exploiting and widening these existing channels, etching the spider-like patterns deeper and deeper into the polar landscape. What makes these features so uniquely unsettling is their bizarrely organic appearance. The central point represents the main vent where the gas finally ruptured the surface, and the radiating, branching legs are the channels carved by the gas as it fragmented through the ice, seeking the path of least resistance to freedom. The pattern is fractal and branching, much like a river delta, a lightning bolt, or the veins in a leaf, all systems where energy is efficiently dissipated through a network. This is why it tricks our eyes so effectively. It follows the same mathematical principles that govern many growth patterns in nature, including those of living things. We are hardwired to recognize these branching, efficient forms, and on a barren planet, our first instinct is to assign them to biology rather than an incredible cryogeological process. The study of these spiders is more than just solving a visual puzzle. It provides a crucial window into the current climate and seasonal cycles of Mars. By monitoring these features year after year, scientists can see them grow and change, providing real-time data on the thickness of the seasonal ice cap, the strength of the sublimation process, and even wind patterns, as the ejected dark material is blown into dramatic dark streaks across the bright ice. This ongoing activity proves that Mars is not a static, long-dead world. It is a planet that still breathes, with a pulse tied to its seasons, where the very air freezes and then violently explodes back into gas, continually reshaping the polar regions in one of the most dramatic and alien geological shows in the solar system. Of course, the search for light doesn't end at the poles. Sometimes it appears in the most unexpected places, sparking debates that reach far beyond the scientific community. On multiple occasions, primarily from the vantage point of the Curiosity rover, navigation cameras have captured something that makes the heart skip a beat: a tiny, brilliant pinprick of light shining on the distant horizon. In one particularly famous image from 2014, this speck of light seems to beam out from behind a rock outcrop, looking for all the world like a distant lamp post or a campfire, a stark and solitary beacon in the immense Martian dusk. In a landscape defined by its profound and ancient silence, the appearance of any light source feels instinctively artificial, an immediate signal of activity in a place we assume to be completely dead. It's an image that effortlessly fuels the imagination, suggesting everything from secret bases to wandering explorers, and it quickly becomes a focal point for those convinced that someone or something is already there. The most probable and scientifically validated explanation for these mysterious glints is both simpler and a testament to the challenging environment our robots operate in. The leading culprit is a cosmic ray hit. Our solar system is flooded with high-energy particles, atomic nuclei accelerated to nearly the speed of light, often originating from distant supernova or our own sun. Mars, lacking a strong global magnetic field and a thick atmosphere like Earth's, has its surface constantly bombarded by this shower of radiation. When one of these tiny, high-speed particles strikes the charge-coupled device, or CCD, of a rover's camera sensor, it deposits a burst of energy. The camera's electronics interpret this sudden jolt of energy exactly as they would a photon of light hitting that pixel, resulting in a single, perfectly bright white or colored pixel in the final image. These hits are random, transient, and entirely a product of the camera's hardware interacting with the deep space environment. They are a form of visual static, a reminder of the hostile radiation bath that any future human explorers would have to contend with. Another compelling natural explanation points to a far more familiar phenomenon, a specular reflection. This is the same principle that causes a distant window to flash in the sun or a piece of glass on a beach to suddenly catch your eye. On Mars, a rock surface with a particularly smooth, flat, and angular face can act like a mirror. If the sun happens to be at precisely the right angle in the sky relative to that rock and the rover's camera, the sunlight can reflect directly off that surface and into the camera lens, creating an intensely bright, focused glint that stands out against the generally dull, non-reflective surrounding terrain. Given the countless thousands of rocks and angles on Mars, it is statistically inevitable that these perfect alignments will occur from time to time, creating a brilliant but completely natural flash that vanishes as quickly as it appears when the sun moves. Despite these logical and well-supported explanations, the persistence of speculation around these lights speaks to a powerful psychological driver in our exploration of the cosmos, the profound desire for connection. An unexplained light on a distant planet is a Rorschach test upon which we project our deepest hopes and fears about the universe. It taps into a fundamental question that has underpinned the space age since its inception. Are we alone? A solitary light feels like a signal, a sign that we are not the only sentient beings pondering the vastness of space. It represents the possibility of contact, the thrill of discovery, and the validation that the human story is part of a larger, galactic narrative. This desire is so strong that it can sometimes override Occam's razor, the principle that the simplest explanation is usually the correct one, leading us to favor extraordinary possibilities over mundane ones. For scientists working on the missions, these images are not dismissed but are treated as valuable data points to be investigated and understood. Each occurrence is scrutinized. Is the bright pixel present in both the left and right navigation camera images taken at the same time? If it only appears in one, it is almost certainly a camera artifact like a cosmic ray hit. Could the sun's position and local topography explain a reflection? This rigorous process of elimination is fundamental to the scientific method. It ensures that every claim is vetted and that truly anomalous phenomena, should they ever be found, are identified with utmost certainty. These brief flashes of light, while ultimately explained by known physics, serve an important purpose. They keep us questioning, they keep us curious, and they remind us that part of the wonder of exploring Mars is the capacity for even its most ordinary processes to create moments of extraordinary and deeply human intrigue. Just when we thought we'd seen it all from dragon scales to ghostly doorways, Mars served up a discovery so whimsical and relatable, it became an instant media darling. In September of 2013, as the Curiosity rover was transmitting a batch of images from its extended mission in Gale Crater, a sharp-eyed enthusiast browsing the public archives noticed something utterly bizarre nestled among the rocks. There, perched on a stone ledge, was what appeared to be a small, furry creature, complete with a rounded body, pointed snout, and even two little ears. It looked for all the world like a relaxed rodent, a Martian guinea pig casually sunning itself on the red planet. The internet, of course, exploded with the Mars rat, and suddenly, the idea of a lonely rodent millions of miles from home became one of the planet's most charming and persistent myths. This adorable encounter is arguably the purest and most delightful example of the psychological phenomenon we've seen repeatedly: pareidolia. This is the brain's automatic and subconscious tendency to impose meaningful patterns, especially faces and familiar forms, onto random and ambiguous stimuli. It's the same mental shortcut that lets us see a smiling face in the front of a car or a dragon in a passing cloud. This instinct is so deeply ingrained because it was a critical survival tool for our ancestors, quickly identifying a potential predator's face in the dappled light of a forest, or recognizing a fellow tribe member's expression from a distance could mean the difference between life and death. When we explore the utterly alien and often monotonous landscapes of Mars, our pattern-seeking brains are working overtime, desperately trying to make sense of the unfamiliar by connecting it to the familiar library of shapes we carry in our minds. What makes the Mars rat so special is not just its cuteness, but the specific type of familiarity it triggers. Seeing a face in a rock is one thing, but seeing a complete, relatable animal is another level entirely. It taps into a deep-seated human affection for and curiosity about other creatures. A rodent is a terrestrial animal, something we associate with life, activity, and even companionship in the case of pets. To project that specific biological form onto a Martian rock reveals our profound desire to find not just signs of life, but life that resembles what we know, life that feels familiar and perhaps even friendly. It transforms a cold, distant planet into a place that feels a little less lonely, a little more like a world we could understand. Scientists, of course, were quick to offer the geological reality behind the illusion. The rat is nothing more than a wind-sculpted rock, and its familiar shape is the product of coincidence and erosion. The relentless Martian wind, carrying its fine, abrasive dust, acts like a master sculptor with an infinite amount of time. It patiently wears away at softer materials, leaving behind more resistant knobs and protrusions. In this case, the process left a small, isolated rock that, from one specific angle and with the right play of shadows, happens to align perfectly with our mental image of a small mammal. It's a testament to the incredible power of wind erosion on a planet with no liquid water or plate tectonics to refresh its surface. The same forces that created the sphinx-like formation carved this tiny, rodent-shaped masterpiece. The legacy of the Mars rat extends far beyond a single funny picture. It serves as a constant, humorous reminder of the crucial difference between perception and reality in scientific exploration. Our brains are superb at generating quick, intuitive hypotheses. That's a rat. But science is the meticulous process of testing those hypotheses against all available evidence. The rover didn't detect any movement, any body heat, or any organic molecules around the rat. The surrounding context showed nothing but barren rock. The scientific conclusion, therefore, is that it's just a rock. This process, initial exciting perception followed by careful, evidence-based analysis, is the very engine of planetary discovery. It ensures that we are guided by data, not just by our hopes and imaginations. Ultimately, the Mars rat is more than a meme. It's a cultural touchstone that brilliantly highlights the human element inextricably woven into our robotic exploration of the solar system. These rovers are built and operated by humans, and their images are pored over by humans around the world. The fact that we can look at a distant planet and see something as heartwarming as a little animal speaks to our boundless creativity and our deep-seated need to connect. It reminds us that our exploration of Mars is a deeply human endeavor, driven not just by cold data collection, but by wonder, curiosity, and a sense of shared adventure. The rat may not be real, but the joy, discussion, and scientific dialogue it inspired certainly were, proving that even an illusion can play a valuable role in bringing us all a little closer to the mysteries of the red planet. If you thought a rodent was a stretch for Pareidolia, Prepare for a discovery that tapped into one of our deepest fascinations, the hunt for giants. In 2014, the Curiosity rover's mastcam captured an image of an object that made paleontologists and space enthusiasts alike do a double take. Lying on the ground, partly buried in the sand, was a long, slender, and strangely segmented object. Its smooth, rounded form and apparent joints looked for all the world like a fossilized spinal column or a massive, bleached whale bone. In the stark emptiness of the Martian desert, the suggestion of such a large biological remnant was both thrilling and eerie, sparking immediate speculation that we had finally stumbled upon the tangible remains of a long-dead Martian megafauna. The reality, as determined by the rover's science team, was far less sensational but no less fascinating from a geological standpoint. This so-called whalebone is almost certainly an unusually shaped rock, carved into its deceptive form by the same patient sculptor responsible for so many of Mars's oddities: wind erosion. The segments or vertebrae are likely the result of differential erosion, a process where a rock composed of layers with varying hardness is exposed to the elements. Softer material between harder layers is worn away more quickly by the abrasive wind, leaving behind a series of ridges and grooves that can create a strikingly segmented appearance. Alternatively, it could be a type of concretion, where mineral-rich groundwater cemented sediments together in a series of nodules within the surrounding rock. When the softer rock around it eroded away, this more resistant, bead-like formation was left behind. It's a natural masterpiece of erosion, not a biological relic. So why are scientists so confident it's not a fossil? The jump from a weirdly shaped rock to a confirmed fossil is a monumental one, requiring a cascade of specific and corroborating evidence. A single, ambiguous shape is never enough. On Earth, paleontologists don't identify fossils by shape alone. They analyze the microscopic structure, the chemical composition, and the geological context. A real bone fossil would have a specific cellular texture preserved in the stone, a telltale porosity and internal structure that is unmistakable to a trained eye with the right tools. It would also be composed of specific minerals like calcium phosphate that commonly replace organic material during the fossilization process. Furthermore, it would almost certainly not be alone. The discovery of a large vertebrate fossil would imply the existence of an entire ecosystem, and you would expect to find other bones, teeth, or associated fossils nearby. The whalebone was an isolated feature with none of this supporting context. This leads to the captivating question: what would real fossil hunting on Mars actually entail? It's a pursuit that would look very different from the hammers and brushes of terrestrial paleontology. The primary instruments would be the incredibly advanced tools already on the rovers, but used with a specific forensic focus. First, a high-resolution camera, like the mastcam or the Mars Hand Lens Imager, would be used to scrutinize the object at an incredibly fine scale, searching for any textures that resemble biological cells, vascular patterns, or other microscopic organic structures. Next, a spectrometer would be deployed to zap the rock with a laser or X-rays, analyzing the elemental composition it gives off in return. A reading showing a significant presence of elements like phosphorus, carbon, and sulfur, the building blocks of life as we know it, would be a major red flag warranting further investigation. The most powerful tool in this hypothetical arsenal would be a close-up chemical analyzer, an instrument like the scanning habitable environments with Raman and luminescence for organics and chemicals, or Sherlock, on the Perseverance rover, is designed for exactly this purpose. It uses ultraviolet lasers to map the distribution of organic compounds and minerals across a rock surface. It wouldn't just detect the presence of organics. It could potentially detect specific molecular patterns that are unlikely to form without biological processes. Finding such a pattern inside a rock with a suspicious shape would be the closest thing to a eureka moment scientists could hope for from a robot millions of miles away. Ultimately, the whale bone serves as a perfect dress rehearsal for the greatest discovery humanity could ever make. It represents the moment our pattern-seeking brains leap ahead of the evidence, a necessary and valuable part of the scientific process that generates excitement and questions. But it also highlights the meticulous, painstaking work that must follow that initial leap. It's a reminder that the search for life on Mars isn't about finding a single monster bone. It's a sophisticated forensic investigation at a planetary scale, requiring us to read the subtle stories written in chemistry and microscopic texture. Every strange rock that tricks our eyes is another test of our methods, sharpening our tools and our minds for the day when we might finally find a shape that is accompanied by the chemical signature that changes everything. Moving from the grand illusions of bones and statues, we arrive at a formation that seems to defy not only logic, but the very laws of physics itself. In a landscape of stark cliffs and rubble, the Curiosity rover once captured an image that made everyone pause. Perched on the edge of a rocky outcrop was what looked unmistakably like a lone spoon, its handle stretching out into thin air, and its bowl poised as if ready to scoop up a helping of Martian soil. The most mind-bending part was that it appeared to be floating, a piece of delicate tableware miraculously suspended against the rusty sky. It was a sight so domestically familiar yet so impossibly out of place that it immediately sparked theories of intelligent design, as if we'd stumbled upon the ruins of a giant's picnic. This seemingly impossible balancing act is actually a brilliant demonstration of the differential erosion, a fundamental geological process where different parts of a rock wear away at vastly different rates. The spoon isn't a separate object at all, but is intricately connected to the larger rock formation it extends from. It's made of a more resilient material, perhaps a layer of hardened volcanic ash or a seam of mineral-rich rock that was more resistant to weathering. Imagine this tough layer sandwiched between much softer, crumbly material like sandstone or clay. For millions of years, the relentless Martian wind, carrying its fine, abrasive dust, has been sandblasting this cliff face. The softer rock erodes away quickly, retreating backward, while the more resilient layer erodes far more slowly. What was once a solid block of stone is gradually sculpted into a precarious fin, and then within that fin, the wind continues its work, carefully carving away the softer material from around the resistant bowl and handle, leaving behind this astonishing, spoon-like silhouette. The illusion that it's floating is a simple trick of perspective and resolution. From the rover's camera angle, we cannot see the slender, rock-hard connection that undoubtedly still tethers the handle of the spoon back to the main cliff. It's the same principle as a cantilevered balcony or a diving board. The structure is anchored at one end, providing the support needed to project the rest of the form out into empty space. Our brains, conditioned by a lifetime of gravity on Earth, see a shape that looks too thin and delicate to support its own weight and assume it must be magically suspended. But on Mars, with only 38% of Earth's gravity, such delicate structures can persist for far longer than they ever could on our own planet, allowing the wind to create these breathtakingly fragile artworks. We don't even have to leave our own world to find stunningly similar examples. Here on Earth, the relentless forces of wind and water have created formations that are every bit as surreal as the Martian spoon. In places like Bryce Canyon in Utah, you can witness a forest of hoodoos, tall, thin spires of rock that protrude from the bottom of arid basins. These spires are often topped with a harder, more resistant capstone that protects the softer column beneath it from eroding as quickly, creating shapes that look like giant stone totem poles or even people. In some cases, the erosion can create natural arches and bridges that seem to defy gravity. The Martian spoon is simply a more isolated and refined example of this universal process. A hoodoo in its late stages of life, whittled down to its most essential and improbable form. The true significance of this delicate spoon is not that it hints at alien diners, but that it serves as a powerful indicator of Martian environmental history. The existence of such a fragile formation tells scientists that the winds in this particular area, while persistent, are not catastrophically strong. A single powerful dust storm or hurricane-force wind would easily topple such a delicate structure. Its continued existence suggests a long period of relatively gentle, consistent erosive forces. Furthermore, the fact that it was formed primarily by wind and not by water speaks volumes about the climate of this region for perhaps billions of years. It's a silent witness to an arid, patient world, where the atmosphere, though thin, has been the primary artist sculpting the landscape for eons. Ultimately, the spoon is a monument to time itself. It represents the incredible patience of natural forces, working not over decades or centuries, but over millions and millions of years. Each grain of dust carried on the Martian wind acts like a microscopic sculptor's chisel, and given enough time, these tiny, imperceptible actions can carve a mountain into a spoon. It's a humbling reminder of the vast, almost unimaginable scales of geological time, where a planet can slowly reveal its history not through dramatic explosions, but through the quiet, persistent whisper of the wind. The spoon will not last forever. One day, its final connection will erode away and it will crumble to dust. But for now, it stands as one of the most elegant and beautiful examples of how nature, with enough time, can create forms of breathtaking delicacy and astonishing illusion. Just as we marvel at the delicate spoon carved by wind, our next discovery speaks to a different kind of human fascination, an obsession with geometric perfection. While navigating the rocky, undulating terrain of Mount Sharp, the Curiosity rover's navigation cameras captured an image that sent the internet into a speculative frenzy. There, on the crest of a distant ridge, stood a stark, impossibly perfect, dark cube. It cast a long, sharp shadow, its edges and corners so precise and angular that it looked utterly artificial against the natural, eroded curves of the Martian landscape. It was the Platonic ideal of a cube, seemingly placed with intention, and for a brief, thrilling moment, it felt like we had stumbled upon evidence of a structure, a monolith, or perhaps even a marker left by some unknown intelligence. This Mars cube, quickly and humorously dubbed the Cubehenge by online sleuths, is a spectacular case study in how our brains are wired to seek out order and structure, especially in chaotic environments. Straight lines and perfect right angles are vanishingly rare in nature. On Earth, when we see them, they are almost always the product of human design: the edge of a building, a street corner, a manufactured object. This association is so strong that it creates a powerful cognitive bias. When presented with an ambiguous shape on an alien world, our minds immediately jump to the most extraordinary conclusion: if it's a perfect shape, it must have been made. This instinct is a double-edged sword. It fuels our imagination and drives exploration, but it also sets the stage for disappointment when a more mundane explanation emerges. That explanation, as provided by the patient scientists at the Jet Propulsion Laboratory, lies in the fascinating interplay of perspective, resolution, and geology. The cube was not a separate object at all, but a small, angular boulder sitting atop a distant hill. The perfect shape was an illusion created by the limitations of the camera that first spotted it. The rover's navigation cameras are essential for planning safe driving routes, but they are relatively low resolution and monochromatic. From miles away, a rock with a roughly blocky shape, when seen from one specific angle and under specific lighting conditions, can appear far more geometrically perfect than it actually is. The long, deep shadow it cast further enhanced the illusion, sharpening its features and hiding any irregularities that would have given away its natural origin. The true nature of the cube was revealed when Curiosity got closer and used its much higher resolution mass cam. The perfect monolith dissolved into what it had always been: a relatively ordinary, water-worn rock, perhaps a piece of hardened bedrock that had eroded out and tumbled downslope. Its shape was more rounded and irregular, like most other rocks in the area. This process of closing in on a mystery is a fundamental rhythm of Martian exploration. An orbital image or a distant navcam shot provides a tantalizing, low-resolution tease that captures the public's imagination. Then, the slow, methodical approach of the rover acts as a focusing lens, gradually replacing speculation with data and wonder with understanding. The cube was never a disappointment. It was a promise of a mystery that was then fulfilled by the scientific process. This particular illusion also taps into a deep and recurring theme in science fiction: the alien monolith. From Arthur C. Clarke's 2001 A Space Odyssey to countless other stories, the image of a perfect, silent, black slab placed on a foreign world is a powerful symbol of alien intelligence, a message or a marker meant to guide or test a developing civilization. The Mars cube felt like a page ripped from that book, a moment where science fiction seemed to bleed into reality. This cultural backdrop is why the image resonated so powerfully. It wasn't just a weird rock. It was an archetype that already lived in our collective consciousness, making the illusion feel strangely familiar and profoundly significant. Beyond the science fiction, the episode highlights a more profound scientific truth about Mars itself. The planet has a natural geology capable of producing surprisingly angular formations. While wind erosion tends to create smooth, streamlined shapes, other processes can and do create blocks and sharp angles. Fracturing is a primary example. As bedrock cools, contracts, or is stressed by Martian seismic activity, it can crack along straight planes, creating natural polygons and blocks. Impact events can also shatter rock into sharp, angular fragments. So, while the cube itself was an illusion of perspective, the fact that there are blocky rocks on Mars is very real. They just aren't the perfect, manufactured cubes our minds so eagerly want to see. The legacy of the Mars cube is a testament to the public's passionate engagement with the journey of exploration. It was a moment of shared mystery that transcended scientific circles, captivating a global audience. It demonstrated that every new image from Mars is scrutinized by millions of eager eyes around the world, all participating in the adventure of discovery. These moments, even when they are debunked, are vitally important. They keep the mission in the public eye, generate excitement, and remind us all that the exploration of Mars is a human story, not just a scientific one. It's a story filled with moments of breathtaking wonder, playful speculation, and the ultimate satisfaction of solving a puzzle together, one carefully beamed image at a time. Leaving behind the geometric illusions of distant cubes, we arrive at a discovery that is both visually spectacular and scientifically rich. A finding that proves reality can be even more wondrous than our imaginations. As the Curiosity rover drilled into a rock slab nicknamed Garden City in 2015, it wasn't just the interior that captivated scientists. It was the stunning field of delicate, spiky formations surrounding the drill hole. This wasn't a monotonous plain of dust and rock. It was a miniature crystal garden, a vibrant patch of Martian soil teeming with intricate, light-toned, jagged minerals that stood in sharp, beautiful relief against the dark, rusty bedrock. These weren't the smooth blueberries of opportunity. These were sharp, complex, and dazzling, looking less like a geological feature and more like a tiny, alien forest of crystalline trees. The secret to this miniature garden lies in the complex dance of chemistry and water that occurred deep within the Martian subsurface billions of years ago. The story begins when this area was likely a lakebed or a zone where groundwater was persistently flowing through layers of saturated sediment. Within this wet environment, different minerals dissolved from the surrounding rock began to circulate. Some of these minerals, likely sulfates like calcium sulfate or magnesium sulfate, became supersaturated in the water, meaning the water was holding more dissolved material than it normally could. This unstable situation needed a trigger to reverse, a change in conditions that would force the minerals to suddenly fall out of solution and solidify. This change could have been a drop in pressure, a shift in temperature, or a change in acidity. When that change happened, the minerals didn't just precipitate as a solid layer. They began to crystallize, growing outward from nucleation points within the pore spaces of the sediment. Imagine the mineral-rich water as a sort of cement slurry flowing through a sponge. The crystals grew slowly, pushing the surrounding sediment grains aside as they expanded, forming veins and nodules with sharp, defined edges. Over immense stretches of time, these crystal-filled veins became harder and more resilient than the surrounding sedimentary rock. Then, much later, the relentless Martian wind began its work, acting like a master etcher. It scoured away the softer, uncemented material, but the hardened mineral veins resisted erosion. The result was this breathtaking landscape in miniature, where the resilient crystals now stand proud, exposed as the intricate, spiky garden we see today. The composition of these crystals is a geochemical treasure trove, a direct record of the ancient fluids that formed them. Instruments like Curiosity's Chemistry and Mineralogy tool, or Chi-Min, are designed to analyze the specific atomic structure of minerals. By identifying whether these light-toned veins are gypsum, basanite, or other sulfates, scientists can start to reverse engineer the properties of the water that once flowed here. The type of mineral that forms is exquisitely sensitive to the water's temperature, salinity, and acidity. Were these crystals born in a warm, neutral spring or a salty, acidic brine? The answer, locked in their crystalline structure, tells us about the habitability of this ancient environment. Some water conditions are more favorable to life than others, and this crystal garden provides a permanent, stone diary entry of what those conditions were. Furthermore, the very presence of such extensive mineral deposition tells a story of longevity. These intricate formations didn't form in a single, catastrophic flood. They are the product of persistent, perhaps episodic, groundwater flow over long periods. This suggests that the wet conditions on Mars weren't just a brief, passing phase. There was enough time, thousands, maybe millions of years, for these slow, delicate chemical processes to create these complex features. This transforms our view of ancient Mars from a world that might have had occasional flash floods to a planet that could sustain a stable, interactive hydrosphere underground, even as its surface dried out and its atmosphere faded away. Ultimately, the Garden City Crystal Garden is more than a beautiful oddity. It's a powerful symbol of the new, forensic level of exploration we are conducting on Mars. We are no longer just taking pictures of landscapes. We are reading the intimate chemical stories written inside the rocks. These spiky, resilient crystals are natural archives, preserving a billion-year-old recipe for Martian groundwater. They show us that the most profound secrets of the Red Planet are often hidden in plain sight, waiting not for a grand monolith, but for a careful, curious geologist with a drill and a laser to come along and listen to the story they have to tell. Amidst a field of jagged, rust-colored rocks, the Curiosity rover once rolled upon an object that seemed to have fallen from another world, because it literally had. Sitting on the Martian surface was a surprisingly smooth, dark, and lustrous rock. Its surface pocked with deep cavities that gave it the appearance of a sculpted metal bar. In a landscape defined by dust and crumbling sandstone, this object's sleek, almost polished appearance made it look utterly out of place, like a piece of industrial debris dropped on an alien construction site. Dubbed Egg Rock by the mission team, this wasn't just another weird stone. It was a visitor from the depths of space, an iron-nickel meteorite that had survived a fiery descent to become a permanent resident of the Red Planet. The reason we find so many of these metallic space rocks on Mars, compared to Earth, boils down to one crucial factor: the atmosphere. Earth is wrapped in a thick, protective blanket of air that serves as a superb defensive shield. When a meteoroid enters our atmosphere, the intense friction and pressure of slamming into all those gas molecules causes it to heat up. often burning up completely in a brilliant streak of light we call a shooting star. Larger objects may survive, but they are dramatically slowed down and often break apart. Their surfaces ablated and melted into a characteristic fused, glassy crust known as a fusion crust. Mars, however, has an atmosphere that is only about 1% as dense as Earth's. This wispy envelope provides almost no braking effect. An incoming meteoroid experiences far less resistance, meaning it doesn't slow down as much and isn't subjected to the same level of intense, surface melting heat. It screams through the thin air and slams into the ground at a much higher velocity, often remaining largely intact. This difference creates a fascinating paradox. While the Martian atmosphere is too thin to breathe or to provide significant protection from radiation, it is just thick enough to act as a final filter. Stony meteorites, which are more fragile, often shatter upon high-speed impact with the Martian surface, leaving behind difficult-to-identify fragments. But tough, dense iron-nickel meteorites like egg rock are built to last. They can withstand the violent journey and the impact, often sitting on the surface for millions of years in a state of remarkable preservation. The cold, dry, and largely non-corrosive environment of Mars means they don't rust away as quickly as they would in a humid Earth environment. Essentially, Mars acts as a perfect natural museum for these metallic relics, collecting and curating them across its surface for our rovers to find. When Curiosity discovers one of these meteorites, its powerful suite of instruments transforms from a geological tool into a planetary analysis kit. The rover doesn't just take pictures, it can press its alpha particle X-ray spectrometer directly against the meteorite's surface. This instrument bombards the target with radiation, and then reads the unique signature of X-rays that are emitted in response, effectively creating an elemental fingerprint. In the case of egg rock and others like it, the readout showed a very distinct signature dominated by iron and nickel, with traces of other metals like phosphorus. This composition is the definitive hallmark of a particular class of meteorite known as an iron, which originates from the core of a shattered planetesimal, a small, protoplanetary body that formed in the early solar system. This is where a simple space rock becomes a time capsule. These iron meteorites are literally pieces of a planetary core. They represent the end product of a process called differentiation, which occurred in the solar system's infancy over 4.5 billion years ago. When a planetesimal was large and molten enough, dense metals like iron and nickel sank to its center to form a core, while lighter silicate minerals rose to form a mantle and crust. By analyzing the precise ratios of metals and isotopes within these Martian meteorites, scientists can peer back in time to understand the conditions and timescales under which these first building blocks of planets formed. Each one is a shattered piece of a world that never was, a sample of the very foundations of our solar system delivered directly to our robotic geologists. The discovery of these common meteorites also provides a crucial, unintended benefit for future human exploration. Iron-nickel meteorites are rich in valuable metals. On a planet where every ounce of material must be shipped from Earth at astronomical cost, the presence of abundant, pre-processed metals sitting on the surface could be a game-changer. They could potentially serve as a readily available resource for early settlers to use for manufacturing tools, constructing habitats, or even providing radiation shielding. A meteorite that tells us about the death of one world might just help enable the birth of a new human presence on another, turning a scientific curiosity into a foundational stone for our future among the stars. From the otherworldly gleam of meteorites, we turn our gaze to an orbital mystery that seems to capture a moment of playful, almost biological movement frozen in time. High above the surface, the powerful cameras of the Mars Reconnaissance Orbiter have spotted peculiar features in the planet's mid-latitudes that look less like geology and more like a snapshot from a primordial pond. These are the so-called Mars tadpoles, Strange formations, each consisting of a rounded, hollowed-out head and a long, trailing tail that often curves and meanders across the landscape. Seen from above, the uncanny resemblance to a swarm of amphibian larvae is undeniable, creating a whimsical and instantly captivating mystery set against the stark Martian terrain. The formation of these tadpole shapes is a story written not by life, but by the relentless forces of wind and, most intriguingly, the fleeting presence of liquid water. Geologists believe the rounded head of the tadpole starts its life as a standard impact crater. When a meteorite strikes the surface, it excavates a bowl-shaped depression and scours a clean, flat floor. This smooth, hard-packed floor becomes the stage for the next act. In Mars's distant past, when the climate was potentially warmer and wetter, these crater floors may have occasionally hosted small, temporary lakes from melting ice or groundwater seepage. This water, rich in dissolved minerals, would have pooled in the crater. As it eventually evaporated, it left behind a layer of cement-like salts and sediments, creating a durable, erosion-resistant cap over the crater floor. This is where the planet's persistent winds take over as the primary sculptor. The surrounding landscape, lacking this hardened protective layer, is composed of much softer, easily eroded material. Over millions of years, the abrasive Martian winds act like a sandblaster, relentlessly scouring and carving the terrain. They wear down the softer material around the hardened crater floor, but the resistant cap protects the crater itself from eroding at the same rate. The result is what geologists call an inverted crater. The once low depression is now a raised mesa, standing proud above the surrounding plains that have been worn away. This resilient mesa becomes the head of our tadpole. But what about the tail? This is the most fascinating part of the puzzle. The prevailing theory points to a powerful, directional flow, most likely of water, but potentially of wind or even lava, that was deflected or channeled by the newly formed mesa. As this flow encountered the obstacle, it would have been forced to divert around it. This diversion concentrated the erosive power of the flow directly downstream of the mesa, carving a deep, narrow channel in its wake. The flow, now focused and energized, continued to cut this channel as it moved away, creating the long, trailing tail that gives the feature its tadpole appearance. The channel might later have been further widened and defined by additional episodes of flow or by continued wind erosion, sharpening the feature into the elegant form we see from orbit. The tantalizing implication here is the role of liquid water. While wind can certainly sculpt and refine these features, the initial carving of a deep, narrow channel is most efficiently done by a fluid with consistent direction and volume, like water. If water did indeed carve these tails, it speaks to a very specific and active hydrological period on Mars. It suggests that after the crater was hardened and raised, there were still episodes where water flowed across the surface, perhaps from seasonal snowmelt or outbursts from underground aquifers. These weren't vast oceans, but more like intermittent streams, yet they had enough power to leave a permanent mark on the landscape, effectively drawing a tadpole's tail behind a hardened crater. The study of these features is more than just solving a cute geological puzzle. It's a way to map the history of fluids on Mars. By analyzing the direction and curvature of thousands of these tadpole tails, scientists can effectively map the ancient flow directions across the planet's surface. This provides critical data for modeling the paleoclimate, helping us understand where water was once moving and from what source it originated. Each tadpole becomes a fossilized arrow, pointing the way water flowed billions of years ago. Their presence adds another layer of complexity to the story of Mars, revealing a world that wasn't just statically wet, but dynamically shaped by flowing liquids that sculpted its surface in surprisingly delicate and intricate ways. They are a beautiful reminder that even the smallest, most transient flows can leave a legacy that endures for eons. But the rover's initial glimpse was just the beginning of the story, a teaser for a spectacle that would only become clearer with time. As Curiosity continued its ascent of Mount Sharp, it returned to the area, capturing new, higher-resolution images of that same geological formation from different angles and under varying light. These fresh perspectives didn't diminish the wonder, they enhanced it. The higher-resolution views revealed the so-called floating spoon in astonishing detail, showing it not as a separate, impossibly balanced object, but as an incredibly delicate fin of rock, still indisputably connected to the larger outcrop by a thin, arching bridge of stone. This connection, invisible from the first vantage point, was the anchor that solved the physics-defying mystery, revealing the spoon for what it truly was, a breathtaking natural cantilever, a testament to the unbelievable durability of certain Martian rock layers. This resilience speaks volumes about the geological history locked within these strata. The spoon's handle isn't made of just any rock. It's composed of a much more resistant material, likely a layer of hardened volcanic ash or a mineral-cemented sandstone that acts as a natural armor. This tough layer was once sandwiched between softer, more crumbly materials. For eons, the relentless Martian wind, carrying its fine, abrasive dust, has acted as a master etcher. It meticulously scoured away the softer material, retreating the cliff face backward, but the resistant layer eroded at a dramatically slower pace. What was once a solid block became a narrow fin, and within that fin, the wind continued its work, carefully undercutting and carving around the most resilient section, leaving behind this miraculously slender, spoon-shaped silhouette. It's a process of subtraction on a grand scale, where the landscape is defined not by what is built up, but by what is patiently worn away. The existence of such a fragile structure also tells a silent story about the Martian environment. This spoon hasn't been toppled by a powerful storm or shaken apart by a marsquak. Its persistence suggests that while the winds here are constant and patient, they are not catastrophically violent. It hints at a long period of relative stability, allowing these delicate features to be carved and to endure, perhaps for millions of years. Furthermore, the dominant role of wind erosion rather than water paints a picture of a landscape that has been bone dry for an immense stretch of time, where the atmosphere, however thin, has been the sole artist responsible for the most striking sculptures. Ultimately, this spoon and formations like it are more than just geological curiosities. They are chronometers made of stone. They represent the awesome, patient power of time itself. Each grain of dust carried on the wind is an imperceptible sculptor's tool, and given enough millennia, these tiny actions can carve a mountain into a masterpiece of delicate balance. It's a humbling reminder that the forces shaping Mars operate on a scale we can scarcely comprehend, where a single feature can tell a story that spans billions of years, a story of enduring strength and patient, relentless artistry. After the delicate cantilevers and whimsical tadpoles, our next feature seems to pluck an organism straight from an earthly tide pool and place it on the rusty Martian soil. The Mars starfish is another delightful gift from our friend Pareidolia, discovered by the Curiosity rover. From a certain angle, a particular rock appeared to possess a central body with 5 stubby, rounded arms radiating outward, mimicking the iconic form of an echinoderm perfectly. It was a moment of pure, playful recognition, a shape so tied to our own planet's biology that it felt wonderfully, bizarrely out of place. This specific instance of pattern recognition is so compelling because it taps into a form we associate with complex, bottom-dwelling marine life. A starfish isn't just a face or a bone. It's a complete, multi-limbed organism. This makes the illusion feel even more concrete, as if we've stumbled upon a fossil frozen in time. Of course, the reality is a testament to the infinite creativity of non-living processes. This starfish is almost certainly a ventifact, a rock that has been meticulously sculpted by wind-blown sand. The prevailing winds in that area, carrying their fine, abrasive particles, have sandblasted the rock for eons, wearing away softer material and polishing harder surfaces. The result is a form whose symmetry isn't biological, but aerodynamic, shaped by the consistent direction of the Martian winds that have smoothed and rounded its features into this familiar, yet entirely accidental, shape. What makes this discovery so valuable, beyond the initial fun of the illusion, is what it represents about the incredible diversity of the Martian rock catalog. The Red Planet is a geological museum showcasing formations born from three powerful sculptors: volcanic, aqueous, and aeolian processes. The starfish falls into the last category, a masterpiece of wind erosion. But just a short drive away, a rover might find a bubbly, vesicular rock full of holes, a clear relic of a volcanic past where gas bubbles were trapped in cooling lava. Elsewhere, it might find a stone riddled with hard, resistant nodules like the famous blueberries that tell a clear story of mineral-rich water percolating through sediments. Each oddly shaped rock is a clue in the planetary detective story. A smooth, streamlined rock suggests it was once tumbled in a flowing river. A pitted, jagged one might speak of a violent volcanic explosion. A fantastically eroded and balanced one, like our earlier spoon, points to eons of patient sandblasting. The starfish isn't a failed fossil, it's a successful ventifact. Its shape is a direct record of the wind's direction, speed, and persistence. By studying such rocks, scientists can map the ancient climate of Mars, understanding how atmospheric circulation patterns have changed over billions of years. So, while our brains delight in seeing a starfish, the true wonder lies in reading the rock's actual story. That one formation tells us that the winds in that specific region blew consistently from one direction for a very, very long time. It's a data point in the grand model of Martian history, a silent witness to the endless, patient forces that have shaped the surface of another world. It reminds us that every strange shape, whether it looks like a spoon, a tadpole, or a starfish, is a sentence in the epic autobiography of Mars, written in the language of geology and waiting for us to translate it. Now we turn from the familiar shapes of starfish and spoons to a discovery that is far more chemically exotic, one that hints at a truly alien form of geology that may have once reshaped the Martian surface. Orbital spectrometers, the incredible instruments that can identify minerals from space by analyzing the light they reflect, have mapped vast regions of Mars coated in unusually bright, sulfur-rich deposits. These aren't the subtle stains we might expect from ordinary weathering. These are brilliant, expansive layers that stand out starkly against the rusty backdrop. For scientists, these bright patches presented a compelling puzzle. Sulfur is a common element, but its concentrated abundance here suggested something far more dramatic than a quiet chemical process. One of the most thrilling hypotheses to emerge is that we might be looking at the ghostly remains of a type of volcano that doesn't exist on Earth. A cryovolcano that erupted not with molten rock, but with liquid sulfur, painting the landscape in a bizarre, brilliant yellow. To understand how a sulfur volcano might work, we have to first forget everything we know about terrestrial volcanism. On Earth, volcanoes are powered by silicate magma, molten rock that erupts at searing temperatures often exceeding 2,000 degrees Fahrenheit. The driving force is heat from radioactive decay and our planet's molten core. A sulfur volcano on Mars would operate on a completely different principles. Instead of being driven by internal heat, it could be powered by the planet's profound cold. The theory suggests that beneath the Martian surface, there could be vast reservoirs of solid sulfur. When this sulfur is warmed not to thousands of degrees, but to a relatively tepid 240 degrees Fahrenheit, it melts into a vibrant red-orange liquid. This heating could be provided by localized geothermal activity, or even by the intense pressure of overlying ice sheets. This liquid sulfur is also incredibly dense, meaning it could easily push its way up through fractures in the crust, just like magma, but at a fraction of the temperature. The eruption itself would be a spectacle unlike any seen on our world. Imagine not a fiery fountain of incandescent rock and ash, but a viscous, oozing flow of bright yellow liquid sulfur creeping across the frozen Martian landscape. As it emerged onto the surface, with its average temperature of -80 degrees Fahrenheit, the liquid sulfur would encounter an environment colder than any industrial freezer. It would instantly begin to freeze and solidify, its surface cracking and fracturing as the interior continued to flow. The result wouldn't be a towering volcanic cone, but likely a low, pancake-like dome or a wide, thin flow, spreading out and quickly solidifying into a vast, glassy sheet of pure sulfur. This entire process, from eruption to solidification, would be eerily silent and devoid of the catastrophic explosions we associate with volcanoes on Earth. A slow-motion geological event playing out in the deep freeze of space. The implications of past sulfur volcanism are profound for the story of Martian habitability. On one hand, sulfur is a fundamental element for all known life. On Earth, certain microbes known as chemolithioeutrophs near deep-sea hydrothermal vents actually eat sulfur compounds, deriving energy from them in a process called chemosynthesis. If similar organisms ever arose on Mars, these sulfur-rich deposits could have been a veritable buffet, providing both a key energy source and a potential building block for life. The hydrothermal systems that might have driven the sulfur to the surface could have also created warm, wet, mineral-rich niches underground, perfect protected habitats for microbial communities to thrive away from the harsh surface conditions. Yet there is a deeply sinister side to this scenario. Sulfur, particularly in the form of sulfur dioxide, is a powerful toxicant and can create highly acidic environments when mixed with water. Widespread sulfur volcanism could have periodically acidified any lakes or shallow seas on the Martian surface, making them inhospitable to any life that wasn't extraordinarily resilient. It could have also released vast quantities of sulfur aerosols into the atmosphere, potentially triggering global cooling events that would have pushed an already cold planet into deeper freezes. So this alien process becomes a double-edged sword. It could have provided the very food for life in the subsurface while simultaneously poisoning the potential for it on the surface, creating a complex and challenging puzzle for astrobiologists trying to determine if Mars was ever truly alive. Ultimately, the search for evidence of these strange volcanoes is about more than just adding a new type of geological feature to the Martian map. It is a direct window into the internal composition and thermal history of the planet. Confirming that sulfur volcanism occurred would tell us that Mars's interior is, or at least was, rich in sulfur in a way that Earth's is not. It would point to a different chemical pathway for the planet's evolution, one where lower temperature geological processes played a much more significant role. Each bright, sulfur-rich deposit seen from orbit is a potential clue, a candidate site for a future rover to visit, drill into, and analyze. Unraveling this mystery would force us to expand our understanding of what volcanism can be, revealing a world where the cold itself became a creative force, sculpting the landscape with a brush of liquid gold. From the hypothetical landscapes painted by sulfur volcanoes, we journey to one of the most beautiful and persistent Martian illusions, a sight that transforms the red planet into a world that seems eerily Earth-like. Each year, as winter's grip loosens on the Martian northern plains, orbital cameras capture a breathtaking transformation. The vast, dark sand dunes near the pole begin to sprout what appear to be sprawling, intricate forests of dark trees, separated by lighter patches of melting frost that look like sun-dappled snow. From high above, the effect is staggering. It doesn't just resemble a boreal forest on a snowy day, it looks nearly identical. This is the Mars tree illusion, a spectacular trick of light, shadow, and seasonal change that has captured the public's imagination for over a decade, offering a fleeting glimpse of a Mars that feels hauntingly familiar. The magic behind this arboreal mirage is a stunningly complex dance between the Martian surface and its atmosphere, driven by the planet's distinct seasons. During the long, dark polar winter, temperatures plummet so low that carbon dioxide from the atmosphere freezes directly onto the surface, forming a slab of clear, solid CO2 ice that can be several feet thick, blanketing the dark sand dunes below. When the sun finally returns in the spring, it triggers a dramatic and alien process. Sunlight penetrates this translucent layer of dry ice and heats the dark sand underneath. This warming causes the bottom of the ice slab to sublimate, transforming directly from a solid into a gas. Trapped between the ground and the still solid ice above it, this gas builds up immense pressure. It doesn't erupt randomly, it seeks out the weakest points in the ice, often at the crests of the dunes where the ice is thinnest. It then bursts through in violent, dark jets, hurling geysers of dark sand and dust high into the thin Martian air. As this material rains back down, it lands on the top of the ice sheet, creating stunning, intricate patterns of dark streaks. The sheer number of these eruptions creates a fractal, branching pattern that, from dozens of miles overhead, is indistinguishable from the trunks and branches of trees radiating outward. The lighter areas between them are simply patches of clean, bright frost that haven't yet been covered by falling sand or have already sublimated away entirely, creating the perfect visual contrast. This phenomenon is a masterclass in how scale and perspective can completely alter our perception. Our brains are exquisitely tuned to recognize the familiar branching patterns of trees and rivers. It's a fundamental aspect of how we navigate and understand our own world. When we see that same pattern repeated on another planet, the cognitive leap to forest is instantaneous and powerful. It's a more sophisticated version of the same Pareidolia that makes us see faces in rocks, but here it's applied to an entire ecosystem, making the illusion feel grander and more credible. The scale is what sells it. Since we have no familiar object for reference in an orbital image, our mind subconsciously assigns a scale based on what it knows. We assume the trees are the size of trees, not realizing we're actually looking at streaks of sand that might be dozens of meters across, on dunes the size of terrestrial mountains. Yet, far from being a scientific distraction, this beautiful illusion has proven to be an incredible tool for public engagement and education. When these images are released, they invariably go viral, sparking wonder and curiosity in people who might not normally follow the latest news from planetary science. That initial moment of mistaken identity becomes a powerful hook, a gateway that draws people in. It creates a shared moment of excitement and questions, which scientists and educators can then leverage to explain the truly fascinating reality. The conversation effortlessly shifts from, "Are there trees on Mars?" to, "Wait, so there are geysers of sand shooting out of carbon dioxide ice, tell me more." In this way, the forests of Mars perform a vital service. They act as a bridge, connecting the public to the more complex, but no less amazing, truths of Martian geology and climatology. They demonstrate that the planet is not a static, dead rock, but a dynamically changing world with active seasonal processes that are both alien and spectacular. The illusion doesn't diminish the science. It amplifies it by providing a relatable entry point into a discussion about sublimation, seasonal ice caps, and aeolian processes. It's a perfect example of how a simple misunderstanding, when investigated, can reveal a reality far more wondrous than the illusion itself, reminding us that the true magic of Mars lies not in finding what we know, but in discovering the processes we have yet to imagine. If you thought the blueberries were a marvel of natural geometry, wait until you get a load of this next find. As the Opportunity rover continued its epic trek across Meridiani Planum, its cameras landed on a rock that looked less like a geological formation and more like a piece of forgotten artillery. Dubbed the Mars Cannonball, this was no ordinary stone. It was a near-perfect sphere, resting on the surface as if it had been carefully placed there by some unseen hand. Its flawless roundness was so precise, so mechanically perfect, that it seemed to defy any natural explanation, instantly conjuring images of ancient battlefields or industrial machinery on a world that has known neither. It was a stark, almost humorous reminder that Mars is a planet that constantly keeps us guessing, presenting us with puzzles that challenge our very understanding of how rocks behave. This incredible sphere is actually one of nature's most fascinating creations, a concretion. Think of it not as a rock that was shaped from the outside, but as one that grew from the inside out. The story begins billions of years ago, when this region of Mars was likely a vast, wet plain, perhaps the sandy bottom of a shallow lake or a saturated layer of sediment beneath the surface. Water, rich with dissolved minerals, percolated through the porous sand. Within that water were dissolved compounds, most notably hematite, an iron oxide mineral. This mineral-rich solution began to seep into the small, empty spaces between the sand grains. Then, a chemical trigger, a change in acidity, a drop in temperature, or a shift in pressure, caused the dissolved minerals to suddenly come out of solution and solidify, much like sugar crystallizing in syrup. But it didn't solidify into a random lump. The process started at a central point, a nucleation site, which could have been a single grain of sand or a tiny fossil. From this central point, the mineral cement, the hematite, precipitated outward in all directions with perfect uniformity. It grew layer upon layer, slowly and evenly, pushing the surrounding sand grains aside as it expanded. Because the chemical conditions were the same in every direction, the growth was perfectly radial, resulting in a stunningly spherical shape. The surrounding sandstone acted like a mold, and the concretion grew to fill it, its form constrained only by the available space and the relentless, even pressure of its own growth. Over immense stretches of time, the softer, uncemented sandstone around this incredibly hard concretion was worn away by the Martian wind, leaving the resilient, perfectly round cannonball sitting proudly on the surface, a monument to a process of patient, chemical self-assembly. We don't even have to leave our own planet to find almost identical objects. In the desert landscapes of the American Southwest, particularly in Utah, you can find virtually the same geological phenomenon. They are known as Maqui marbles, and they are strikingly similar to their Martian cousins. These terrestrial concretions are also composed of a hard iron oxide shell, often surrounding a softer sandstone core. They formed through the exact same process on Earth, where iron-rich groundwater moved through the Navajo sandstone, cementing the grains into these perfect spheres. The main difference is simply their mineralogy. Where the Martian cannonballs are rich in hematite, the Maqui marbles are typically made of goethite, another iron-bearing mineral. Holding a Maqui marble in your hand is the closest we can get to touching one of these Martian marbles, a tangible link between the geological processes of our world and the distant, rusty plains of Mars. The significance of these spherical wonders extends far beyond their captivating appearance. For planetary scientists, they are not mere curiosities. They are hyper-accurate record-keepers of ancient environmental conditions. The specific minerals that form the concretion are a direct chemical signature of the water that created them. By analyzing their composition, we can determine the pH, salinity, and temperature of that ancient Martian groundwater. Was it a benign, neutral environment conducive to life? Or was it a harsh, acidic brine? The answer is locked inside the crystalline structure of the sphere. Furthermore, their very existence is proof of persistent, stable water flow. Concretions don't form in a sudden flood. They require a long-lasting, saturated environment where mineral-rich water can circulate for thousands, if not millions, of years. This suggests that these areas of Mars weren't just briefly wet. They were sopping, groundwater-rich environments for extensive periods, dramatically expanding the potential window for habitability. Ultimately, the Mars Cannonball is a beautiful testament to the universality of physical and chemical laws. It shows us that the same processes that shape our own world are also at work, and have been at work, on worlds hundreds of millions of miles away. A phenomenon we can walk out into the Utah desert and witness with our own eyes also occurs on the stark plains of an alien planet. This perfect sphere, which so easily tricks us into seeing something artificial, is in fact one of nature's most elegant and reliable sculptures. It requires no designer, only time, chemistry, and the patient, unwavering laws of physics, proving that even the most seemingly engineered objects can be the magnificent and spontaneous work of a natural world. Leaving behind the perfect spheres and cannonballs, we soar high above the surface for a view of a feature that looks less like geology and more like a mythological beast forever frozen in the Martian act of striking. In orbital images of the vast, dusty plains, scientists have spotted a truly bizarre formation, a dark, sprawling central blob from which dozens of long, sinuous tendrils radiate outward, curling and twisting across the landscape. This Mars jellyfish, with its uncanny resemblance to a medusa floating in a sea of rust, is a stunning and initially baffling sight. It seems both biological and violent, a splash of dark ink that has been smeared across the planet's skin. But this is no alien life form, it is the exact opposite. It is the spectacular signature of a very recent and very violent death from above. This incredible formation is the calling card of a fresh impact crater. The dark, central blob is the crater itself, its newly exposed subsurface material appearing much darker than the surrounding, dust-blanketed terrain. The long, graceful tendrils are what geologists call the ejecta blanket. When a meteoroid slams into the ground at tens of thousands of miles per hour, it doesn't just create a hole. It vaporizes itself and a large amount of the target rock, generating an unimaginably powerful shockwave. This force instantly liquefies and excavates tons of material, hurling it outward in a high-arc ballistic trajectory. On a planet with an atmosphere like Earth, this ejecta would be slowed and scattered by air resistance. But on Mars, with its incredibly thin atmosphere, the ejected material follows a much cleaner, more predictable path, often landing in beautiful, flowing patterns that record the physics of the impact itself. The most striking aspect of these patterns is their fluid appearance, which is where the jellyfish gets its name. This happens because of a phenomenon called fluidization. The energy of the impact is so immense that it doesn't just throw solid rocks. It melts subsurface ice and layers of loosely packed, water-rich sediments. This creates a slurry of molten rock, water, and debris that acts more like a liquid than a solid as it surges across the landscape. This superheated slurry flows outward with tremendous force, scouring the surface and carving those long, runnel-like channels that form the tentacles. The darker color persists because this excavated material comes from beneath the planet's ubiquitous layer of reddish dust, and it hasn't had enough time to be recovered and bleached by the relentless deposition of new dust. It is a raw, open wound on the planet's surface, and its dark color is a testament to its youth. For planetary scientists, discovering a fresh crater like this is like finding a newly printed page in the history book of the solar system. The primary value of these features lies in their use as a cosmic clock. The surface of Mars, like that of the Moon, is a museum of impact scars. The longer a surface has been exposed, the more craters it will accumulate. By counting the number of craters of various sizes in a given area, scientists can estimate its age, a technique called crater counting. A heavily cratered landscape is ancient, while a smooth, uncratered plain is geologically young. A fresh crater, one with sharp rims and dark ejecta, provides a critical data point. It tells us the current impact rate. By studying how many of these fresh craters appear over a set period, we can calibrate our entire understanding of Martian geological history, fine-tuning our estimates of when oceans dried up or volcanoes ceased to flow from billions of years to within a few million. This ongoing process of impact gardening means that Mars is anything but a static museum piece. It is a dynamically changing world, still being actively shaped by external forces. Every year, new meteoroids find their way through the thin atmosphere and leave their mark. Monitoring these events helps us understand the present-day hazards of the Martian environment, a critical consideration for future human explorers. A habitat wouldn't need to worry about a direct hit from a massive asteroid, but a shower of smaller impact ejecta could pose a real risk to structures and equipment on the surface. By studying the frequency and distribution of these fresh impacts, we can better assess these risks and plan for them. The jellyfish, in all its beautiful, terrifying glory, is more than just a geological oddity. It is a reminder that the solar system is a dynamic shooting gallery, and Mars, lacking our protective atmospheric shield, is still on the firing line, its surface continually being rewritten by the random violence of space. After the violent, explosive artistry of impact craters, we encounter a formation that feels almost architectural in its precision, a discovery that looks less like a natural wonder and more like a waffle iron was pressed into the Martian soil. From the vantage point of orbit, the high-resolution imaging science experiment camera aboard the Mars Reconnaissance Orbiter captured an image of a truly peculiar feature in the planet's southern hemisphere. There, spread across the landscape, was a nearly perfect grid of raised, intersecting ridges, creating a series of hollow, square-like depressions. The Internet, with its endless appetite for the bizarre, immediately dubbed it the Mars Waffle, and for good reason. Its geometric perfection was so striking that it seemed to defy any simple explanation of wind or water erosion, inviting wild speculation about everything from ancient city foundations to landing pads. This remarkable pattern is actually a spectacular example of a geological formation known as boxwork. To understand how it forms, we need to travel back in time to a period when this region of Mars was geologically hyperactive, likely dominated by volcanism. The story begins deep underground, where a massive body of molten rock or magma was slowly cooling and solidifying. As it cooled, it contracted, a process that created an extensive network of fractures and cracks throughout the newly formed rock. These fractures weren't random. They followed the natural stress lines within the cooling mass, often creating a remarkably regular, grid-like pattern of weakness, much like the crazing that appears in drying mud or the cracks in an old painting. The next chapter of the story involves water. Hydrothermal fluids, heated by the same volcanic system that produced the magma, were circulating through these deep fractures. These superheated waters were rich with dissolved minerals leached from the surrounding rock. As they flowed through the fracture network, they deposited these minerals, often hard, resilient compounds like silica or iron oxides, lining and cementing the cracks, effectively turning them into solid veins of much harder material. For millions of years, this mineral-infused water continued to seep through, slowly but surely building up these veins, making them significantly more resistant to erosion than the surrounding, softer rock that housed them. The final act, which reveals the waffle pattern we see today, is one of exhumation. The entire area was likely buried under subsequent layers of volcanic ash or sediment for eons, protecting it. But eventually, the overlying material was stripped away by the relentless forces of wind erosion. The softer rock, the one that hadn't been mineralized, was easily scoured away by the abrasive Martian winds. But the incredibly hard, cemented veins that filled the ancient fractures were far more durable. They resisted the erosion, remaining proud of the surface as an interconnected network of ridges. What was once a network of weaknesses underground became a network of strengths on the surface. The hollows of the waffle are the areas where the soft rock was removed, and the raised grid is the resilient mineral filling that was once hidden deep within the fractures. This process highlights a fascinating and counterintuitive principle in geology. Sometimes, the most durable and long-lasting features on a landscape start their lives as zones of weakness. The fractures were the Achilles heel of the original rock mass, but by being infused with strengthening minerals, they were utterly transformed. The resulting boxwork is a kind of inverse fossil, not a cast of a long-gone organism, but a cast of a long-gone fracture system. A perfect mineralized skeleton of the stresses that once shaped the Martian subsurface. It's a permanent record of the planet's fiery, watery, and windy past, all etched into a single, breathtaking formation. The significance of the waffle extends beyond its good looks. For planetary geologists, such features are like a Rosetta Stone for deciphering the history of groundwater and volcanic activity on Mars. The specific minerals that make up the ridges can tell scientists about the temperature and chemistry of the hydrothermal fluids that once flowed there. This information is crucial for mapping where life might have had a chance to survive deep underground, protected from the harsh surface conditions. Furthermore, the sheer scale and regularity of the boxwork provide clues about the size and intensity of the volcanic system that spawned it, helping to piece together the thermal history of this region of the planet. Ultimately, the Mars waffle is a powerful testament to the ability of natural, physical processes to create structures of astonishing regularity and beauty without any guiding intelligence. It demonstrates that the universe operates on a set of physical laws that often favor efficiency and order, producing patterns from the hexagonal columns of the giant's causeway to the branching veins of a leaf, that repeat across scales from the microscopic to the planetary. It's a humbling reminder that nature is the ultimate engineer, capable of crafting geometries that, while they may appear designed to our pattern-seeking eyes, are simply the emergent result of patience, chemistry, and the immutable laws of physics playing out over billions of years. Just when we thought we'd seen every animal the Martian imagination could conjure, from rats to starfish, the red planet offered up one of its most delightfully detailed illusions yet. Perched conspicuously on a rocky slope, a formation captured by the Curiosity rover appeared to show a stoic, watchful iguana, its head tilted slightly, with a textured back, and even the suggestion of legs tucked beneath its body. The resemblance was so uncanny, so instantly recognizable, that it felt for a moment as if a desert reptile had hitched a ride to another world. This Mars iguana immediately scampered across the internet, another charming example of how our minds insist on populating an alien landscape with familiar forms, turning inert geology into a scene brimming with perceived life. This specific instance of Pareidolia is so compelling because of the incredible resolution of the rover's cameras. We aren't looking at a grainy, distant blob. We're examining a high-definition image where individual grains of sand and the subtle textures of rock are visible. This wealth of detail is a double-edged sword. On one hand, it provides scientists with an unprecedented tool for geological analysis, allowing them to discern the finest layers in a cliff face or the precise mineralogy of a pebble. On the other hand, that very clarity provides our pattern-seeking brains with more fodder for misinterpretation. Our visual cortex, a masterpiece of evolutionary engineering, is constantly performing lightning-fast analyses, scanning for threats, resources, and other living creatures. When presented with a complex, high-resolution image from an alien environment, it works overtime, assembling random shapes, shadows, and textures into a coherent, familiar whole. The knobby protrusion becomes a head, the line of darker rock becomes a spine, and the play of light across a rough surface suggests scaly skin. The brain isn't trying to deceive us, it's simply doing its job with supreme efficiency, using its terrestrial database to make sense of the utterly foreign. For the scientists operating the rovers, these public reactions to images like the iguana are not a nuisance but a celebrated feature of the mission. Each viral rock represents a massive surge in public engagement, a moment where planetary science captures the global conversation. This excitement is the lifeblood of publicly funded exploration. It translates into continued support, inspires the next generation of engineers and geologists, and fulfills a core mission objective: to share the adventure of discovery with everyone on Earth. The mission teams understand that the initial, fanciful interpretation is the hook. It's the doorway through which millions of people willingly step, eager to learn more. That collective, what is that? Moment is the starting pistol for a global conversation about Mars, and scientists are thrilled to be the ones to guide it from speculation to understanding. And that guided journey is where the real magic happens. When a Mars iguana captures the public's imagination, planetary geologists seize the opportunity to become educators. They calmly and clearly explain the actual processes at work, using the viral image as a perfect teaching tool. They'll point out how the iguana is a textbook example of differential erosion, where a more resistant layer of rock, perhaps a mineral-hardened vein, has weathered at a much slower rate than the softer materials surrounding it. The wind, carrying its fine, abrasive dust, has patiently sculpted the formation over millennia, undercutting sections and leaving others proud, accidentally carving a shape that pushes all our biological recognition buttons. This shift in narrative, from a potential life form to a masterwork of Aeolian art, doesn't diminish the wonder, it redirects it. The story becomes about the incredible forces that shape planets, the patience of geological time, and the fascinating ways in which non-living processes can mimic life so convincingly. Ultimately, the legacy of the Mars iguana and its many animal-themed cousins is a testament to the collaborative nature of modern exploration. It represents a beautiful partnership between human intuition and robotic precision, between public curiosity and scientific explanation. Our innate tendency to see a lizard in a rock is the spark, the emotional connection that draws us in. The rover's cameras provide the detailed evidence, the raw data from another world. And the scientists provide the context, translating that data into a deeper understanding of Martian processes. This cycle of wonder, evidence, and enlightenment is how we collectively explore. It reminds us that every strange rock, whether it looks like a spoon, a face, or an iguana, is an invitation not to believe in Martian reptiles, but to participate in the slow, careful, and profoundly rewarding process of unraveling the true secrets of the red planet. Amidst the chaotic jumble of rocks and sand, the Curiosity rover's lens once focused on an object that felt like it had tumbled straight out of a steampunk fantasy. There, lying partially embedded in the soil, was a rock that looked unmistakably like an old-fashioned, oversized skeleton key. It had a long, straight shank and a perfectly formed, intricate bow at one end, complete with what appeared to be a classic, notched design. It was a moment of surreal cognitive dissonance, a symbol of human entry and security, sitting abandoned on a world without a single door to unlock. This Mars key instantly felt significant, as if we'd stumbled upon a prop from a cosmic fairy tale, a literal key to a mystery we had yet to even imagine. The formation of this incredible simulacrum is a masterclass in the chaotic, yet sometimes miraculously aligned, forces of erosion. This key was not carved or forged, but born from a series of chance geological events playing out over millions of years. The process likely began when a crack or a vein of harder, more resilient mineral formed within a larger, softer rock. Perhaps it was a seam of quartz or hematite deposited by ancient groundwater, snaking its way through a block of softer sandstone. This harder vein acted as a form of natural reinforcement. Then, the primary sculptor of Mars, the wind, went to work. The relentless, sand-blasting winds scoured the landscape, effortlessly wearing away the softer material. But the mineralized vein resisted, eroding at a much slower pace. The wind didn't just work from one direction, it swirled and shifted, undercutting some areas and polishing others, occasionally exploiting a pre-existing fracture or a soft spot in the rock. Through this incredibly patient and random process, the softer material around the tough vein was gradually, grain by grain, stripped away, leaving the more durable key standing in stark relief until it eventually broke free and came to rest on the surface. Its shape wasn't designed, it was revealed, a durable skeleton exposed by the dissolution of its softer surroundings. This phenomenon forces us to confront a fascinating question. Why do we so consistently see human artifacts? The answer lies in a concept called the cultural Rorschach test. Our perception is not a perfect recording of reality. It is a constructive process heavily influenced by our personal experiences and the shared symbols of our society. A person from a culture that has never used metal keys would likely look at the same rock and see something entirely different, perhaps a strange animal or a celestial symbol. But for us, the key is an archetypal object, deeply embedded in our collective consciousness. It symbolizes secrets, access, discovery, and solutions. When our pattern-seeking brains are presented with an ambiguous shape on an alien world, they don't randomly generate comparisons. They dip into this vast cultural library and pull out the most visually and symbolically resonant match. The brain isn't just saying, "This looks like a key." On a deeper level, it's whispering, "This looks like the answer." This instinct to anthropomorphize and culturalize the Martian landscape is a powerful, double-edged sword. On one hand, it is the very engine of public engagement and wonder. It transforms a dry geological process into a relatable story, making the science accessible and thrilling to millions. It's the hook that draws people into the deeper, more complex narrative of planetary formation. But on the other hand, it presents a significant challenge for clear scientific communication. The initial, exciting interpretation, "It's a key," it can spread like wildfire, while the more nuanced, factual explanation, "It's a wind-eroded, mineralized vein," struggles to capture the same viral attention. This creates a gap between public perception and scientific reality that researchers must constantly work to bridge, transforming moments of mistaken identity into valuable teaching opportunities about the incredible, if less sensational, power of natural forces. Ultimately, the Mars key is not a puzzle to be solved, but a mirror to be looked into. Its significance lies not in what it tells us about Mars, but in what it reveals about ourselves. It is a testament to our boundless creativity, our deep-seated need to find narrative and meaning in the chaos of the universe, and our enduring desire to feel connected to the cosmos, even if that connection is woven from the threads of our own imagination. The key doesn't unlock a door on Mars. It unlocks a door in our own minds, inviting us to marvel at the sheer coincidence that natural forces on a distant world could, for a fleeting moment, reflect a symbol so intimately and uniquely human. Navigating the rocky terrain of Mars, the Curiosity rover has beamed back images filled with enough strange geometry to keep even the most skeptical minds entertained. And in 2014, it delivered one of its most charmingly urban illusions. Perched within a chaotic jumble of rocks on the slopes of Mount Sharp was a formation that looked, for all the world, like a standard earthly traffic signal. 3 near perfectly aligned circular discs, one on top of the other, stood out against the cliff face, their placement and spacing so unnervingly precise that the internet immediately and affectionately dubbed it the Mars traffic light. It was a moment of delightful absurdity, a mundane earthly object seemingly transplanted onto an alien mountainside, and it perfectly captured the playful relationship between the serious work of science and the public's boundless imagination. Geologically, this peculiar triple feature is a brilliant example of how Mother Nature can, with enough time and the right tools, create near-perfect geometric patterns without any blueprint at all. Scientists quickly identified the most likely explanation. These circular features are almost certainly nodules of a much harder mineral, most likely hematite, similar to the famous blueberries found by the Opportunity rover. The process begins when mineral-rich groundwater percolates through a layer of soft, sedimentary rock. The dissolved minerals, in this case iron oxide, begin to precipitate out of the water and solidify around a central nucleus like a grain of sand. They grow concentrically, layer by layer, in all directions, forming a perfectly spherical concretion. Because the chemical conditions are uniform, the growth is beautifully symmetrical. In the case of the traffic light, it's believed that a cluster of these concretions formed close together within the same rock layer. Over millions of years, the softer surrounding sandstone was meticulously scoured away by wind erosion, leaving the incredibly resilient, sphere-shaped nodules exposed and protruding from the cliff face. Their alignment is simply a matter of chance, a happy accident of where they happened to form within the sedimentary bed before it was eroded. Another compelling, though less likely, geological explanation involves a process known as mineral staining. On Earth, water dripping down a cliff face can carry dissolved minerals like iron or manganese. As the water slowly trickles down, it can deposit these minerals in repeated, circular patterns, creating dark, stained spots that can sometimes align vertically. On Mars, a similar process could have occurred billions of years ago when liquid water was more prevalent on the surface. Water seepage from a crack or overhang above could have deposited minerals in a series of drops, leaving behind a vertical pattern of stained circles that closely resembles a traffic signal. While the concretion theory is generally favored for its prevalence in the region, the mineral staining hypothesis illustrates that there are often multiple natural pathways to create even the most artificial-looking features. What makes the traffic light so special, however, isn't the geology itself, but the human reaction to it. The scientists at NASA, a jet propulsion laboratory, far from dismissing the public's whimsical interpretation, have consistently embraced the humor and engagement these moments generate. They understand that a traffic light on Mars is a powerful gateway drug to science. It's an image that is instantly understandable and shareable, a moment of levity that draws people into a conversation they might otherwise scroll past. The JPL team has even been known to play along, with official social media accounts occasionally making lighthearted references to these discoveries. This approach doesn't undermine their work, it enhances it. It demonstrates that scientists are not just cold, analytical robots, but people with a sense of humor who are thrilled to share the joy of discovery with the world. It builds a bridge of accessibility, showing that you can be both rigorously serious about data and wonderfully playful with interpretation. This episode, like the Mars rat or the iguana, serves as a gentle reminder of the beautiful dichotomy at the heart of Martian exploration. Our initial, pattern-seeking reaction, it's a traffic light, is the hook, the spark of curiosity that makes us stop and look. The scientific explanation, a story of mineral-rich water, spherical concretions, and eons of wind erosion, is the fulfilling meal that follows. One is not more valuable than the other. They work in tandem. The wonder pulls us in, and the science rewards our curiosity with a deeper, more profound understanding of the universe. The Mars traffic light didn't ultimately control interplanetary traffic, but it did successfully green-light a global conversation about geology, perception, and the sheer, unexpected fun of exploring another world. Perhaps one of the most personally resonant and eerily human illusions ever beamed back from the red planet was captured not by a high-resolution orbiter, but by the aging Spirit rover in 2007. As it surveyed the rocky, undulating landscape of the Gusev crater, its panoramic camera snapped an image of a distant hill. There, perched on a ridge, was a solitary, dark figure. It had a distinct head, shoulders, and a torso that seemed to taper down, appearing for all the world like a person sitting on a rock, gazing out contemplatively over the Martian wilderness. The Mars woman, as she was instantly dubbed, became an icon. She wasn't a face or an animal, she was a silhouette, a sentient-seeming presence that felt less like a rock and more like a lonely explorer, a silent witness to our robotic invasion of her world. The creation of this powerful illusion is a masterclass in the interplay of light, shadow, and the limitations of technology. The Spirit rover's cameras, while revolutionary for their time, were a fraction of the resolution of the instruments we use today. From the rover's vantage point hundreds of meters away, the woman was just a handful of pixels across. At such a distance, fine details are completely lost. What we are seeing is not a detailed form, but a simplified silhouette where light and dark areas blend into a single, ambiguous shape. The figure itself is likely just a dark, irregular boulder or an unusually shaped rock outcrop. The magic happens because of its position on the skyline. The low angle of the sun in the Martian sky cast a long, deep shadow behind it, effectively merging the rock's base with its own shadow and eliminating any visual cues that would anchor it to the ground. This isolation against the bright sky turned a simple rock into a free-floating, humanoid apparition. This specific illusion taps into a psychological phenomenon far deeper than simple pareidolia. It engages our capacity for narrative. A face or a starfish is a pattern, but a human silhouette in a contemplative pose is a story. Our brains don't just recognize a shape, they instantly fabricate a context. Who is she? Why is she there? Is she resting, waiting, watching us? This impulse to create narrative around ambiguous stimuli is a fundamental part of human cognition. We are storytelling creatures, and we are particularly drawn to stories that feature ourselves. A human form on another planet is the ultimate story. It suggests companionship, mystery, and a shared experience across the cosmos. It transforms Mars from a sterile collection of minerals into a potential stage for drama, making the planet feel strangely relatable and hauntingly lonely all at once. The Mars woman also represents a fascinating evolution in our relationship with these Martian illusions. Earlier mysteries like the face on Mars were often met with fervent belief in artificial origins, sometimes bordering on conspiracy. But by 2007, the public had become more sophisticated. While the image certainly sparked excitement and wonder, the prevailing reaction was one of amused recognition rather than fervent belief. The conversation quickly shifted from "is it an alien?" to "wow, that really looks like a person." This marks a subtle but important shift in our collective understanding. We were beginning to appreciate these moments not as potential evidence to be argued over, but as delightful curiosities that reveal the fascinating quirks of our own perception and the clever ways nature can trick us. Ultimately, the silhouette on the ridge serves as a poignant Rorschach test for our species. In that handful of pixels, we don't see what is actually on Mars. We see a reflection of our own hopes, our loneliness, and our enduring desire to find ourselves in the universe. The Mars woman is a ghost, a projection of our own humanity onto an alien landscape that is utterly indifferent to our stories. She reminds us that the greatest mystery we are exploring on Mars is not just the planet's past, but the inner workings of the human mind itself, and our profound, unshakable need to feel that even in the vast, empty silence of space, we are not entirely alone. And so we come to the final, and perhaps the most profound, mystery on our list, one that cannot be seen or photographed, but only sensed. It is a ghost in the Martian atmosphere, a whisper of a gas that has ignited one of the most intense and enduring scientific debates in modern planetary science, the case of Martian methane. Unlike a rock that looks like a face or a spoon, this enigma is a chemical one, detected by the most sensitive instruments on our rovers and orbiters. It's a puzzle that strikes at the very heart of our quest, because the question it poses is as simple as it is monumental. Is this gas a sign of something living on Mars right now? The story begins with data, painstakingly collected over years. NASA Curiosity rover, acting as a mobile chemistry lab deep within Gale crater, has repeatedly sniffed out tiny, intermittent puffs of methane in the Martian air. We're not talking about vast clouds. The concentrations are minuscule, often measured at around 1 part per billion. To put that into perspective, you'd have to sort through 1 billion molecules of Martian air to find just a single molecule of methane. That these delicate instruments can detect such a faint signal from millions of miles away is a triumph of engineering. But the real shock isn't the detection itself, it's the pattern. The methane doesn't linger as a constant background gas. It appears suddenly, spikes dramatically, and then vanishes without a trace. It's as if Mars is briefly exhaling and then holding its breath again for months or even years. This intermittency is the first major clue that something dynamic and hidden is happening beneath the sterile surface. So why does this cause such a stir? Because on Earth, the vast majority of atmospheric methane is produced by biological processes. It's belched by cows, released by decaying vegetation in wetlands, and leaked from natural gas reserves formed from ancient organic matter. Certain types of microbes, known as methanogens, actually breathe out methane as a waste product. These hardy organisms don't need oxygen. They thrive in places utterly hostile to most life, like deep underground rocks, the guts of animals, or the acidic vents of hot springs. If you were to design a potential biosignature, a chemical signal that could indicate life, methane would be very high on the list. Its fleeting appearance on Mars is therefore electrifying. It's the tantalizing possibility that we are detecting the metabolic waste products of a hidden, subsurface Martian microbiome, a community of microbes quietly going about its business deep below the frozen, radiation-blasted surface. Yet, the universe is rarely so simple, and science demands we rule out all non-biological explanations before we make any extraordinary claims. The fervent debate over Mars's methane is a beautiful example of the scientific process at work, with brilliant minds arguing for a compelling geological alternative. The leading abiotic theory involves a process called serpentinization. This occurs when certain iron-rich minerals in volcanic rock, like olivine, come into contact with water. This chemical reaction produces a new type of mineral called serpentine, and as a byproduct, it also releases, you guessed it, methane. Mars has plenty of the right rocks and is known to have vast deposits of subsurface water ice. The theory suggests that small, sporadic interactions between liquid water and these minerals deep underground could be producing the methane, which then seeps up through cracks and fissures to briefly leak into the atmosphere before it is quickly destroyed by the harsh ultraviolet radiation from the sun. This creates a fascinating detective story with two prime suspects. Is the culprit biology, a silent, living ecosystem, or is it geology, a complex but sterile chemical reaction? The evidence is maddeningly ambiguous. The intermittent nature of the plumes could support either case. Life might be metabolizing in fits and starts, or geological aquifers might only occasionally see the right conditions for serpentinization. Even more perplexing, the European Space Agency's Trace Gas Orbiter, a spacecraft specifically designed to map atmospheric gases from orbit with incredible sensitivity, has largely failed to confirm Curiosity's ground-level detections. This discrepancy itself is a mystery. It could mean the methane is so dilute and short-lived by the time it mixes into the global atmosphere that the orbiter misses it. Or it could suggest the rover itself is occasionally releasing the gas, a possibility the team has rigorously investigated and largely ruled out. The resolution to this mystery will not come from a single, dramatic piece of evidence, but from a slow, careful accumulation of data. Future missions will be key. They will need even more sensitive spectrometers to map the gas's distribution and track it back to its source regions. They might even be able to analyze the carbon isotopes within the methane molecules. Life on Earth prefers to use the lighter carbon-12 isotope over the heavier carbon-13. If the Martian methane is also significantly enriched in carbon-12, it would be a powerful, though still not conclusive, pointer toward a biological origin. Until then, the methane mystery remains wide open. It is the perfect capstone to our journey through the strange and wonderful discoveries on Mars because it embodies the essence of exploration. It is a persistent, tantalizing clue that we cannot yet fully explain. A whisper from the red planet that refuses to be ignored, reminding us that the greatest discoveries are often those that raise more questions than they answer. And so our incredible journey across the rust-colored plains and through the deep valleys of Mars comes to a close, for now. We've encountered a world that constantly dances on the line between the eerily familiar and the profoundly alien. From the grand illusion of a human face staring into the cosmos to the fleeting, mysterious whispers of methane gas that just might be a signature of life. We've marveled at nature's patient artistry in the form of wind-carved spoons and perfect stone spheres. And we've stood in awe of its raw power in the explosive jets that paint giant spiders across the polar ice. Each of these 30 strange discoveries, whether a trick of light and shadow or a definitive chemical clue, represents a different piece of the vast puzzle that is the red planet. What's truly remarkable is how these findings range from delightful distractions to legitimate scientific revolutions. Some, like the adorable Mars rat or the stoic Martian woman, are beautiful reminders of how our own human minds work, forever seeking patterns and stories in the unknown. They may not rewrite textbooks, but they capture our imagination and draw us into the conversation. Others, however, are anything but illusions. The hematite blueberries and the delicate crystal flowers are hard evidence of a watery, potentially habitable past, while the ghost dunes and dragon-scaled terrain tell a dramatic story of a world that lost its atmosphere and its oceans. Each one, from the smallest pebble to the largest orbital formation, is a data point in the epic biography of Mars, a sentence in a story we are only just learning to read. This entire exploration stands as a powerful testament to human curiosity and ingenuity. Every single one of these mysteries was uncovered not by astronauts walking the surface, but by robotic extensions of ourselves, intrepid rovers and watchful orbiters that are the products of decades of engineering and scientific passion. They are our eyes and our hands on a world millions of miles away, and they have fundamentally transformed Mars from a distant red dot in a telescope into a real place with a complex and breathtaking history. The search is far from over. With every answer we get, a dozen new questions emerge, and that is the most exciting part of all. Future missions will delve deeper, equipped with even more sophisticated tools to drill, analyze, and perhaps one day even return samples to Earth, bringing us closer than ever to answering that ultimate question: are we alone in the universe? The adventure is just beginning, and you are a part of it. Your wonder and your curiosity are what drive this exploration forward, so we want to hear from you. Look back through these 30 strange things: the doorways, the jelly donuts, the traffic lights, and the tadpoles. Which one captured your imagination the most? Which discovery made you stop and think, or filled you with a sense of awe? Share your favorite in the comments below and tell us why it fascinates you. Let's keep the conversation going. Remember to like this video if you enjoyed our tour across Mars, and subscribe so you don't miss our next journey into the mysteries of our incredible cosmos. Thanks for watching.